Right now, as you hear this, a spacecraft 590 million kilometers from Earth is staring into an abyss that should not exist. NASA's Juno probe circles a world so massive it could swallow 1,400 Earths. So violent that every second it generates magnetic storms powerful enough to strip the atmosphere from a planet. So alien that the pressure inside its body would crush diamonds into vapor. Jupiter. For decades we believed we understood this gas giant. A ball of hydrogen and helium, a failed star, a cosmic shield protecting Earth from asteroids. The textbooks were confident. The models were clean. But in 2024, Juno peered beneath Jupiter's clouds and transmitted data that shattered every assumption. Deep inside Jupiter, there is no solid surface, no rocky core. Instead, an ocean exists. But not water. Something far stranger. An ocean of liquid metal. Hydrogen compressed so violently by gravity that its electrons tear free from their atoms and flow like an electrical current. This ocean is 30,000 kilometers deep. It churns, it conducts, and it generates the strongest magnetic field in the solar system except for the Sun itself. This is not the Jupiter you were taught about. Juno's instruments detected something even more disturbing. The core scientists expected to find at Jupiter's center might not exist. Gravity measurements suggest that heavy elements, the rock and ice that should have formed a solid kernel, have dissolved. They are floating somewhere inside that ocean of metallic hydrogen. Jupiter's interior is not layered like Earth. It is diffuse, fuzzy, as if the planet's heart has been stirred into oblivion by forces we cannot fully comprehend. But the data became truly inexplicable when Juno measured Jupiter's magnetic field. The field is not symmetric. The northern hemisphere generates a completely different magnetic signature than the southern hemisphere. There is a region near the equator called the Great Blue Spot, where magnetic intensity concentrates without explanation. The field itself is 20,000 times stronger than Earth's. It stretches across 21 million kilometers of space. If you could see it with your eyes, it would appear larger than the full moon from Earth's surface. Jupiter acts like a pulsar. It broadcasts radio waves across the solar system. When those waves were first detected in the 1950s, astronomers thought they were picking up alien signals. They were wrong, but only technically, because what generates those signals is a mechanism so violent, so extreme, that it operates on the boundary between planetary science and astrophysics. And then there is Io, Jupiter's innermost large moon. On December 27, 2024, Juno's infrared imager recorded the most powerful volcanic eruption ever observed. In the solar system, a hotspot larger than Lake Superior, temperatures exceeding those of any terrestrial volcano. Energy output 6 times greater than all of Earth's power plants combined. The eruption is still active, still vomiting lava and ash into space. And beneath Io's cooled crust, Juno detected something no one predicted. Still warm magma, a subsurface ocean of molten rock that has not solidified. Io is not cooling, it is being continuously tortured by Jupiter's gravity. 59 million kilometers farther out, Europa drifts through Jupiter's radiation belts. Its ice surface is smooth, cracked, shifting. Beneath 15 kilometers of frozen water lies an ocean. A real ocean. Liquid water. Twice the volume of all Earth's seas combined. That ocean is salty, chloride-rich. It might be habitable. Water vapor plumes erupt from cracks in the ice and spray into space. If those plumes connect to the deep ocean, they could carry organic molecules. They could carry life itself. This is what Juno found. This is what no one saw coming. Jupiter is not a gas giant. It is a magnetic dynamo wrapped around an ocean of conducting metal. It is a planetary system where moons are simultaneously frozen and volcanic, where radiation sterilizes surfaces while oceans beneath may harbor biology, where storms larger than Earth have raged for centuries without dissipating, where the laws of physics operate at extremes that expose how little we understand about the universe. The discoveries Juno transmitted in 2024 and 2025 do not fit into existing planetary formation models. They suggest that Jupiter's early history was far more chaotic than anyone predicted. Mathematical models now indicate that 4 billion years ago, Jupiter was twice its current size. Its magnetic field was 50 times stronger. Something caused it to contract. Something caused it to settle into its present configuration. We do not know what that something was. What we do know is this: Jupiter is not stable. It is shrinking at a rate of approximately 1 centimeter per century. It is cooling by roughly 1 degree Celsius every million years. The metallic hydrogen ocean inside is still churning, still generating magnetic chaos, still interacting with the moons in ways that produce phenomena we are only beginning to document. This video will take you inside Jupiter. Not metaphorically. We will descend through the atmosphere. We will pass through the transition zone where hydrogen stops being a gas and becomes a supercritical fluid. We will enter the metallic ocean where electrons flow like water and magnetic fields twist into geometries that should not be physically possible. We will examine the core that might not exist. We will explore the radiation belts that would kill any human in seconds. And we will confront the implications of what all of this means for our understanding of planetary formation, magnetic field generation, and the possibility of life. In the solar system, Jupiter has always been visible in Earth's night sky. Ancient civilizations worshipped it. Modern astronomers cataloged it. But Juno revealed it, and what it revealed is terrifying. Prepare yourselves. We descend. You are falling, not through air, not through water, through hydrogen, the most common element in the universe. But hydrogen under conditions so extreme that it stops obeying the rules you learned in chemistry class. You have descended past the swirling storms and the ammonia ice crystals, past the Great Red Spot, a hurricane larger than Earth that has been spinning for at least 400 years. You are 100 kilometers deep. The temperature around you is 0 degrees Celsius. The pressure is already 10 times what you would feel standing at sea level on Earth. You keep falling. At 300 kilometers depth, the pressure climbs to 24 times Earth's atmospheric pressure. The hydrogen surrounding you is no longer a gas. It is becoming denser, thicker. The temperature rises to 150 degrees Celsius. You are still in what scientists call the troposphere, the outermost layer of Jupiter's atmosphere. But atmosphere is the wrong word. There is no boundary between gas and liquid here. No surface where you could stand. The hydrogen simply becomes more and more compressed as gravity pulls you downward into the planet's interior. At 1,000 kilometers deep, the pressure reaches 1,000 bars. 1,000 times the pressure at Earth's surface. The thermometer reads 1,000 degrees Celsius. This is the limit of Juno's microwave radiometer. The instrument can peer through Jupiter's clouds to this depth by measuring the faint microwave radiation that escapes from the interior. Beyond this point, the spacecraft cannot see. But mathematical models allow scientists to predict what should exist deeper down. The models were wrong. You continue falling, 20,000 kilometers into Jupiter. The pressure is now 2 million times Earth's atmospheric pressure. The temperature soars past 8,000 degrees Celsius. Hot enough to vaporize any known metal. Hot enough to ionize most elements into plasma. And here, something extraordinary happens to the hydrogen surrounding you. The atoms are crushed so tightly together that their electrons can no longer remain bound to individual nuclei. The electrons tear free. They flow throughout the liquid like an electric current passing through copper wire. The hydrogen has become metallic. This is not a metaphor. This is not an approximation. The hydrogen has transformed into a substance that conducts electricity like iron or aluminum. It is liquid. It is hot. It is under pressure that would collapse any structure ever built by human engineering. And it fills most of Jupiter's interior. An ocean 30,000 kilometers deep. An ocean that has never seen sunlight. An ocean that generates the strongest planetary magnetic field in the solar system. Scientists have known about metallic hydrogen since the 1930s. The physicist Eugene Wigner predicted its existence based on quantum mechanics. He calculated that under sufficient pressure, hydrogen would undergo a phase transition and become a conductor, but it took until 2017 for researchers to create metallic hydrogen in a laboratory. The experiment required compressing hydrogen to pressures exceeding 4 million times Earth's atmospheric pressure using diamond anvil cells. The sample was microscopic. It existed for only a fraction of a second before the pressure was released and the hydrogen returned to its normal state. Inside Jupiter, metallic hydrogen is not a laboratory curiosity. It is the dominant form of matter. More than 80% of the planet's mass exists in this exotic state. The ocean churns with convection currents, driven by heat escaping from the interior. The liquid metal circulates from hot regions near the core upward toward cooler regions near the surface. This circulation generates electrical currents. Those currents produce magnetic fields. And those magnetic fields create the magnetosphere that extends 7 million kilometers into space and stretches all the way to Saturn's orbit. But Juno discovered something that should not be possible. When the spacecraft arrived at Jupiter in July 2016, one of its primary objectives was to map the planet's gravitational field with unprecedented precision. Gravity reveals mass distribution. By measuring tiny variations in how strongly Jupiter's gravity pulls on the spacecraft during each close flyby, scientists could determine where mass is concentrated inside the planet. Dense regions would pull harder, less dense regions would pull more weakly. The gravity map would reveal Jupiter's internal structure. The scientists expected to find a core. According to every model of planetary formation, gas giants like Jupiter begin as rocky and icy cores that form through collisions of smaller bodies called planetesimals. Once the core reaches a critical mass, roughly 10 times the mass of Earth, its gravity becomes strong enough to capture hydrogen and helium gas from the surrounding protoplanetary disk. The gas accumulates rapidly. Within a few million years, a gas giant is born. The core remains at the center. Dense, solid, permanent. Jupiter's core should contain between 5 and 15 times Earth's mass in heavy elements. Rock, metal, ice. The core should be distinct, sharply defined. When Juno measured Jupiter's gravitational field, the data should have revealed a clear concentration of mass. At the planet's center, the data revealed something else entirely. Jupiter's core is diluted, fuzzy. The heavy elements that should be concentrated at the center appear to be dissolved throughout a much larger region. Gravity measurements suggest that rock and metal extend from the center outward to perhaps half of Jupiter's radius, 25,000 kilometers of diffuse heavy elements, mixed with hydrogen and helium. This is not a core in any conventional sense. This is erosion on a planetary scale. The discovery forced scientists to reconsider everything they thought they understood about Jupiter's formation and evolution. One possibility is that Jupiter never had a sharply defined core to begin with. Perhaps the planet formed through a process called pebble accretion, where small icy particles gradually accumulated without ever creating a distinct rocky kernel. The heavy elements would have been mixed with hydrogen from the very beginning. The planet would have grown by slowly gathering material from the protoplanetary disk rather than by rapid gas capture onto a solid core. But pebble accretion creates its own problems. The process is too slow. The protoplanetary disk around the young sun dissipated within a few million years. There would not have been enough time for Jupiter to reach its current mass through gradual accumulation. The planet had to form quickly. That requires a massive core to trigger runaway gas capture. A second possibility is even more disturbing. Jupiter did form with a solid core, but something destroyed it. Recent theoretical work suggests that core erosion can occur inside gas giants through a process involving the metallic hydrogen ocean. Computer simulations show that almost all heavy elements will dissolve in liquid metallic hydrogen under the right conditions of temperature and pressure. Carbon, oxygen, nitrogen, silicon, iron. Even rock can dissolve like sugar in water. The solid core gradually erodes from its outer surface inward. Heavy elements diffuse upward into the metallic hydrogen layer. Over billions of years, the entire core can be distributed throughout a much larger volume. This process explains Juno's observations, but it raises a new question. What caused the erosion to begin? One hypothesis involves a massive collision early in Jupiter's history. Theoretical models now indicate that roughly 3.8 million years after the solar system formed, Jupiter was approximately twice its current radius and had a magnetic field 50 times stronger than today. Something caused the planet to contract. Mathematical calculations based on the orbital dynamics of Jupiter's tiny inner moons Amalthea and Thebe reveal this primordial state. If a large planetary body collided with Jupiter during this period, the impact energy could have heated the core enough to accelerate its dissolution. The collision hypothesis fits with other evidence. Jupiter's unusually high metallicity compared to the Sun suggests that the planet accumulated more heavy elements than would be expected from capturing solar composition gas. A collision with a massive rocky or icy body would have delivered additional heavy elements to Jupiter's interior. But no one can prove the collision occurred. No direct evidence exists. The event would have taken place 4 billion years ago, when the solar system was still chaotic and violent. Planetary migration was ongoing. Large bodies were still wandering through the inner solar system. A collision with Jupiter is plausible. But so are other scenarios. Another possibility involves layering within Jupiter's interior. If stable layers of fluid exist at certain depths, they could act as barriers that prevent convection from mixing heavy elements throughout the metallic hydrogen ocean. These layers might have broken down over time due to changes in temperature or pressure gradients. Once mixing began, core erosion would have accelerated. The truth is that scientists do not know which explanation is correct. Juno's gravity measurements provide extraordinary detail about Jupiter's current internal structure, but they cannot reveal the processes that created that structure. The spacecraft cannot see into the past. What is certain is this: Jupiter does not have the core that planetary formation models predicted. The heavy elements are distributed throughout a vast region of the interior. This dilution has profound implications for understanding how gas giants form, how their magnetic fields evolve, and how planetary systems develop around other stars. Researchers at the University of Edinburgh published findings in 2025 demonstrating that carbon, nitrogen, and oxygen can form stable molecules within metallic hydrogen. Compounds like methane with 6 hydrogen atoms, or even methanol-like structures. These hypermolecules contain far more hydrogen than would be stable under normal conditions. Their existence suggests that chemistry inside Jupiter is far more complex than anyone imagined. Heavy elements are not simply dissolved in an inert metallic fluid. They are reacting, bonding, creating exotic compounds that have never been synthesized in any terrestrial laboratory. The implications extend beyond Jupiter. Observations of exoplanets have revealed thousands of gas giants orbiting other stars. Many of these worlds are hot Jupiters, massive planets orbiting extremely close to their parent stars. Their interiors must be even more extreme than Jupiter's. If core erosion and exotic chemistry occur inside our own solar system's gas giant, these processes must be universal features of planetary evolution. But understanding Jupiter's interior structure is only the beginning. The dissolved core has another consequence, one that was never predicted by any model. It affects the generation of Jupiter's magnetic field in ways that created one of the most bizarre discoveries Juno transmitted back to Earth. The magnetic field itself is broken. Jupiter's magnetic field should not look the way it does. On Earth, the magnetic field is simple, elegant. The iron core generates a dipole field with magnetic north at one pole and magnetic south at the other. Field lines emerge from the south magnetic pole, arch through space, and converge on the north magnetic pole. There are local variations, small anomalies caused by mineral deposits in the crust. But the overall structure is clean, predictable, a bar magnet buried inside a rotating sphere. Scientists expected Jupiter's magnetic field to follow the same pattern. Stronger, certainly. The planet rotates once every 9 hours and 55 minutes. The metallic hydrogen ocean circulates rapidly, generating enormous electrical currents. Those currents should produce a powerful dipole field aligned roughly with Jupiter's rotational axis. The math was straightforward. The predictions were confident. Juno measured the field during its first close flyby in August 2016. The spacecraft passed within 4,200 kilometers of Jupiter's cloud tops. Its magnetometer recorded field strength and direction with unprecedented precision. The data transmitted back to Earth showed something impossible. Jupiter's magnetic field is asymmetric. The northern hemisphere generates a magnetic field completely different from the southern hemisphere. In the north, the field is lumpy, irregular. Patches of intense magnetism cluster near the pole. In the south, the field is smoother, more organized. The difference is so extreme that it appears as if two separate dynamos are operating inside the planet, one in the north, one in the south. They are not synchronized. They are not symmetrical. They are generating magnetic chaos. Near Jupiter's equator, Juno discovered a region that scientists named the Great Blue Spot. This is not a storm. It is not a physical feature visible in any wavelength of light. It is a localized zone where magnetic intensity reaches values far higher than anywhere else at the same latitude. The Great Blue Spot sits at the equator. It does not rotate with the planet's cloud layers. It remains fixed in position relative to Jupiter's deep interior, and no one knows why it exists. The magnetic field strength at Jupiter's cloud tops measures 20,000 times stronger than Earth's surface field. At the poles, the intensity increases even further. Juno's instruments recorded field strengths approaching 2,000 millitesla. For comparison, a strong refrigerator magnet produces about 10 millitesla. An MRI machine used in hospitals generates 1,000 to 3,000 millitesla. Jupiter's magnetic field at the poles approaches the intensity of medical imaging equipment. But it extends across millions of cubic kilometers of space. This field is not static. It pulses, it fluctuates. It interacts with the solar wind in ways that produce radio emissions detectable from Earth, when astronomers first discovered Jupiter's radio waves in the 1950s. They measured signals at frequencies around 20 megahertz. The emissions were periodic, pulsing with Jupiter's rotation period. The pattern was so regular that some researchers briefly wondered if they were artificial, if they represented transmissions from a technological civilization. They were wrong about the source. But they were not wrong about the strangeness. Jupiter broadcasts radio waves across a spectrum, ranging from kilohertz frequencies up to gigahertz. These emissions are generated by processes that occur when charged particles spiral along magnetic field lines and crash into Jupiter's upper atmosphere. The particles accelerate to nearly the speed of light. When they collide with atmospheric molecules, they release energy as electromagnetic radiation. This is the same mechanism that creates Earth's auroras. But on Jupiter, the process operates at scales that dwarf anything terrestrial. Jupiter's auroras are permanent. They never stop. They form glowing ovals around both magnetic poles. The emissions are brightest in ultraviolet and X-ray wavelengths, but they also glow in visible light and infrared. The auroras are 10 times brighter than Earth's northern lights. They are 100 times more energetic. The charged particles dumping energy into Jupiter's atmosphere deliver more power than the planet receives from sunlight. And the source of those particles is not the solar wind. On Earth, auroras are triggered by solar storms. When the sun releases a burst of charged particles during a coronal mass ejection, those particles travel through space and interact with Earth's magnetosphere. Some particles penetrate the magnetic field and funnel toward the poles where they collide with atmospheric nitrogen and oxygen, creating the shimmering curtains of green, red, and purple light visible from high latitudes. Jupiter's magnetosphere deflects the solar wind 7 million kilometers away from the planet. The bow shock, where Jupiter's magnetic field collides with the solar wind, forms a barrier that prevents solar particles from reaching the atmosphere. So the charged particles fueling Jupiter's permanent auroras must come from somewhere else. They come from Io. Jupiter's innermost large moon orbits just 422,000 kilometers from the planet's center. That places Io well within Jupiter's magnetosphere, well within the radiation belts, well within the region where magnetic field lines rotate with the planet's 9-hour period. Io's surface is covered with volcanoes. More than 400 active volcanic vents. They erupt continuously, spewing sulfur dioxide gas into space at velocities exceeding Io's escape velocity. The gas forms a torus around Jupiter, a donut-shaped cloud of sulfur and oxygen ions that encircles the planet at Io's orbital radius. Jupiter's magnetic field ionizes this gas, strips away electrons, traps the charged ions in the magnetosphere, forces them to co-rotate with the planet. The plasma density in the Io torus is extraordinarily high, orders of magnitude greater than anywhere else in the magnetosphere. And as the magnetic field rotates past Io during each orbit, it scoops up more material. Millions of kilograms per day, that material gets accelerated to high velocities, funneled along magnetic field lines toward the poles, slammed into the atmosphere. The result is a permanent auroral display powered not by the sun, but by a volcanic moon. But Juno revealed another source of particles, another mechanism feeding the auroral engine, one that involves processes occurring deep inside Jupiter itself. The metallic hydrogen ocean is not uniform. Temperature variations create convection cells, rising plumes of hot metallic fluid, descending currents of cooler material. These flows generate electrical currents on enormous scales. The currents interact with the existing magnetic field through a process called magnetic induction. Moving conductive fluid generates new magnetic fields. Those new fields reinforce or oppose the original field depending on the geometry of the flow. This is how dynamos work. Earth's outer core is liquid iron rotating and convecting beneath a solid mantle. The motion generates our magnetic field. Jupiter's dynamo operates on the same principle, but with far more vigorous circulation. The metallic hydrogen layer extends from perhaps 20,000 kilometers depth, all the way down to 50,000 kilometers or deeper. The entire region churns, convex, conducts, and generates magnetic field continuously. But the asymmetry in Jupiter's field suggests that the dynamo is not operating uniformly throughout the interior. Scientists at the University of Rochester studied metallic hydrogen samples created in laboratory experiments using powerful lasers. They measured the electrical conductivity of the material at different temperatures and pressures. Their results revealed something crucial. Metallic hydrogen's conductivity increases dramatically as temperature rises. Hotter metallic hydrogen conducts electricity far more efficiently than cooler metallic hydrogen. This finding has profound implications for understanding Jupiter's magnetic field. If temperature variations exist within Jupiter's metallic hydrogen ocean, those variations will create regions of high conductivity and regions of lower conductivity. The dynamo will operate more vigorously in the hotter, more conductive zones. Those zones will generate stronger magnetic fields. Cooler regions will contribute less to the overall field structure. Juno's gravity measurements revealed that Jupiter's interior is not uniformly mixed. The diluted core region contains more heavy elements than the surrounding metallic hydrogen. Heavy elements change the thermal properties of the fluid. They affect how heat flows through the interior. The result is a complex three-dimensional pattern of temperature variations that creates corresponding variations in magnetic field generation. The asymmetry between north and south hemispheres might result from a large-scale convection pattern that preferentially transports heat toward one hemisphere. Or it might indicate that stable fluid layers exist at certain depths, partitioning the interior into separate regions that generate independent magnetic contributions. The Great Blue Spot might be a region where hot metallic hydrogen rises from deep in the interior, creating a localized zone of intense dynamo activity. Or it might be connected to the distribution of heavy elements in the diluted core region, where higher concentrations of dissolved rock and metal alter the fluid dynamics. No one knows which explanation is correct. Current computer models cannot simulate Jupiter's interior with sufficient detail to reproduce the observed magnetic field structure. The physics is too complex. The scales are too vast. The equations that govern magnetohydrodynamics, the interaction between electrically conducting fluids and magnetic fields, are some of the most difficult in all of physics to solve. What scientists do know is that Jupiter's magnetic field is changing. Observations of Jupiter's radio emissions dating back to the 1950s show variations in intensity and frequency over time. The changes occur on timescales of years to decades. They indicate that the magnetic field itself is evolving, shifting, reorganizing. On Earth, the magnetic field flips polarity every few 100,000 years. North becomes south. South becomes north. The process takes several thousand years to complete. During the transition, the field becomes chaotic, weak. Multiple magnetic poles can exist simultaneously. Some researchers have suggested that Jupiter's asymmetric field might indicate the planet is in the middle of a polarity reversal. The northern and southern hemispheres are reorganizing. The dynamo is transitioning from one stable configuration to another. If true, this would represent an extraordinary opportunity to observe a process that on Earth is known only from magnetic signatures frozen into ancient rocks. But the idea remains speculative. Juno has been observing Jupiter for less than a decade. Magnetic field reversals take thousands of years. Even if a reversal is underway, detecting it would require monitoring Jupiter's field continuously for centuries. The magnetosphere Jupiter's field creates is the largest continuous structure in the solar system after the heliosphere. It extends 21 million kilometers from the planet. If you could see it with human eyes, it would appear as large as the full moon from Earth, despite being over 600 million kilometers away. The magnetosphere is shaped like a teardrop, compressed on the sunward side by the solar wind, stretched into a long tail on the night side that extends beyond Saturn's orbit. Inside this vast cavity, charged particles are trapped and accelerated to relativistic velocities. Jupiter's radiation belts contain electrons and protons moving at significant fractions of light speed. The particle energies are so high that they would penetrate several centimeters of solid lead shielding. Any spacecraft passing through these belts risks catastrophic electronics failures. Any human exposed to this radiation would receive a lethal dose within seconds. Juno survives by flying a polar orbit that passes over Jupiter's north and south poles, while avoiding the most intense radiation near the equator. Even so, the spacecraft is slowly being destroyed. Each close pass exposes its electronics to radiation that causes cumulative damage. Some instruments have already begun to malfunction. The mission is living on borrowed time. But before Juno fails, it continues to transmit data that challenges every model of planetary magnetic fields. Data that suggests magnetic chaos is not an anomaly. It is a fundamental feature of gas giant planets. Data that reveals the interior of Jupiter is far more dynamic, far more violent, and far more alien than anyone predicted. The broken magnetic field is a window into processes occurring 50,000 kilometers beneath the cloud tops. Processes that involve exotic states of matter, extreme pressures and temperatures, convection on planetary scales, chemistry that creates molecules never seen on Earth. Jupiter is not a simple ball of gas. It is a dynamo, a laboratory where physics operates at conditions we can barely simulate, a world where the boundary between matter and energy blurs, where magnetic fields become so intense they can tear apart atoms, where the distinction between solid, liquid, and gas loses meaning. And beneath all of it, deeper than any instrument can probe, something might still exist. Not a core in the conventional sense, but a central region where the temperature and pressure reach values so extreme that new physics takes over, where quantum effects dominate, where matter transitions into states that have no names. Juno cannot see into those depths. No spacecraft ever will. The pressure would crush any probe long before it reached the center. The heat would vaporize any material. The magnetic field would disrupt any electronics. Jupiter's heart will remain forever hidden. But the magnetic field it generates tells us the heart is restless, churning, unstable. And the chaos is spreading outward through the metallic ocean toward the surface. For 400 years, humanity observed Jupiter from Earth. Telescopes revealed bands of clouds, swirling storms, the Great Red Spot. Astronomers mapped the equatorial region in exquisite detail. They cataloged wind speeds exceeding 400 kilometers per hour. They watched storms merge and split and persist for decades. They documented a planet whose atmosphere was in constant, violent motion. But no one had ever seen Jupiter's poles. The geometry of observation made it impossible. Jupiter's rotational axis is tilted only 3 degrees relative to its orbital plane. From Earth's perspective, we see Jupiter almost equator on. The polar regions remain hidden, tilted away, invisible. Even the Voyager spacecraft that flew past Jupiter in the late 1970s passed by the equatorial plane. They captured stunning images of the banded atmosphere. They discovered volcanic eruptions on Io. They revealed the thin ring system. But the poles remained unexplored. Juno changed that. The spacecraft's orbit is polar. Every 53 days, Juno plunges from high above Jupiter's North Pole. Screams past the cloud tops at 200,000 kilometers per hour and emerges over the South Pole before climbing back into the outer reaches of its elliptical path. This trajectory was chosen specifically to avoid the most intense radiation belts near Jupiter's equator. But it provided an unexpected gift. The first detailed views of Jupiter's polar regions. What Juno revealed should not exist. At Jupiter's North Pole, a massive cyclone sits directly over the rotational axis. The storm is 4,000 kilometers across, roughly the size of Earth's continental United States. Winds spiral counterclockwise at speeds exceeding 350 kilometers per hour. The storm has been there since Juno arrived in 2016. It shows no signs of weakening, no signs of moving. It is locked to the pole like a spinning top. But that central cyclone is not alone. Surrounding it in a precise hexagonal formation are 8 additional cyclones. Each storm is roughly 4,000 to 6,000 kilometers in diameter. They orbit the central cyclone, they maintain their positions relative to one another, they form a geometric pattern so regular it appears artificial, and they have persisted for at least 9 years without merging or dissipating. At Jupiter's South Pole, the pattern is different. The central cyclone is similar in size and intensity, but surrounding it are only 5 cyclones instead of 8. They form a pentagonal arrangement. The storms are slightly larger than their northern counterparts. The geometry is different, but the persistence is the same. These storms are permanent features. Nothing like this exists anywhere else in the solar system. On Earth, hurricanes form over warm tropical oceans. They drift with prevailing winds. They are solitary. When 2 hurricanes approach each other, they either merge into a single larger storm or they push each other apart through a phenomenon called the Fujiwara effect. They do not orbit each other in stable geometric formations. They do not cluster around the poles. Earth's poles are too cold to sustain hurricanes. The Coriolis force that drives storm rotation weakens near the poles. Hurricanes that drift too far north or south lose their structure and dissipate. Jupiter's polar cyclones defy these rules. The storms exist at latitudes above 80 degrees. They are confined to a narrow belt within 10 degrees of each pole. They do not migrate toward the equator. They do not expand outward. They remain locked in their geometric arrays year after year. Scientists have been tracking them using Juno's JunoCam visible light imager and the Jovian infrared auroral mapper since 2016. The storms drift slowly. Each cyclone gradually moves toward the pole through a process called beta drift. This is the same process that drives hurricane motion on Earth. The Coriolis force interacts with the cyclone's wind pattern, creating a net drift poleward. But on Earth, hurricanes dissipate before reaching the poles. They require warm, moist air to sustain themselves. As they move into colder regions, they lose their energy source. The storm structure breaks down. On Jupiter, there is no warm ocean. There is no solid surface. The atmosphere is hydrogen and helium gas extending thousands of kilometers deep. The temperature at the cloud tops is minus 150 degrees Celsius, yet the cyclones persist. The answer lies in Jupiter's rotation rate and internal heat. Jupiter rotates once every 9 hours and 55 minutes. This is 2.5 times faster than Earth. The rapid rotation creates an intense Coriolis force. That affects atmospheric motion at all latitudes. Even near the poles, the Coriolis force remains strong enough to sustain rotating storms. On Earth, the Coriolis force approaches 0 at the poles. On Jupiter, it remains significant. But rotation alone cannot explain the geometric arrays. Jupiter generates internal heat. The planet is slowly contracting. Gravity pulls the interior inward. This compression releases energy. Jupiter radiates roughly twice as much energy into space as it receives from the Sun, That internal heat drives convection throughout the atmosphere. Hot gas rises from deep in the interior. It reaches the cloud tops. It radiates energy into space and cools. It sinks back down. This convective circulation provides a continuous energy source for atmospheric dynamics. Near the poles, the combination of rapid rotation and internal heat flux creates conditions that can sustain permanent cyclones. The storms do not require warm tropical oceans. They feed on heat rising from Jupiter's interior. And because there is no seasonal variation, because Jupiter's axial tilt is nearly zero, the heat flux remains constant. The storms have no reason to weaken. They spin forever. But why do they arrange themselves in geometric patterns? Researchers tracking the cyclones over multiple years noticed something crucial. The storms interact with each other through their surrounding wind fields. When two cyclones drift too close together, the wind shear between them creates a repulsive force. The storms push each other apart. This prevents them from merging. But when they drift too far apart, the pressure gradient between the storms creates an attractive force. They pull back together. The result is a self-organizing system. The cyclones settle into configurations where the repulsive and attractive forces balance. At the North Pole, 8 cyclones can fit around the central storm while maintaining stable separations. At the South Pole, only 5 fit. The difference might be related to subtle variations in the depth of the atmosphere, or the strength of the Coriolis force between northern and southern hemispheres. Or it might be connected to the asymmetric magnetic field, creating different plasma densities in the ionosphere above each pole. No computer simulation predicted this behavior. Models of Jupiter's atmosphere assumed that storms near the poles would be chaotic, transient, short-lived. The hexagonal and pentagonal arrays were completely unexpected. When the first images from Juno were released in 2017, planetary scientists struggled to explain what they were seeing. The geometry was too precise, too stable. It looked designed. Some researchers compared the pattern to convection cells in boiling water. When you heat a pot of water from below, hexagonal circulation cells spontaneously form on the surface. Hot water rises in the center of each cell. Cool water sinks at the boundaries. The cells pack together in a regular pattern. This is called Rayleigh-Benard convection. It is one of the most fundamental patterns in fluid dynamics. But Jupiter's polar cyclones are not convection cells. They are rotating vortices. They have distinct circulation patterns. They are separated by regions of different wind speeds and directions. The comparison to Rayleigh-Benard convection is superficial. Other scientists suggested the cyclones might be related to wave patterns in the atmosphere. Rossby waves are large-scale oscillations in atmospheric flow that result from the Coriolis force. On Earth, these waves drive the jet stream. They create meanders in the flow of air from west to east. On Jupiter, Rossby waves might interact with the polar vortices to lock them into specific geometric configurations. But Rossby wave theory cannot fully explain the observations either. The mathematics predicts different numbers of vortices than what Juno observed. The theory suggests the patterns should be unstable on timescales of months, yet the cyclone arrays have persisted for years. The truth is that planetary scientists still do not understand why Jupiter's polar cyclones form these geometric patterns. Current atmospheric models lack the resolution to simulate the small-scale turbulence that might govern the interactions between storms. The equations that describe rotating fluid dynamics on a sphere are notoriously difficult to solve. Even with the most powerful supercomputers, researchers cannot fully model Jupiter's atmosphere. What is known is that the cyclones are not shallow features. Infrared observations using Juno's JIRAM instrument reveal that the storms extend deep into Jupiter's atmosphere. Temperature measurements show cold cloud tops surrounded by warmer regions. The temperature contrasts indicate vertical circulation reaching at least 100 kilometers below the visible cloud layer. The storms might extend even deeper, penetrating into the water cloud layer 500 kilometers down or further into the high-pressure hydrogen atmosphere beyond. The cyclones are also incredibly violent. Juno's close flybys captured images showing the storm structure in exquisite detail. The central cyclones contain smaller vortices within them, substorms swirling inside the main circulation, spiral bands of clouds. regions of intense lightning activity. The turbulence is fractal, chaos nested within chaos. Zooming in reveals ever finer structures. No matter how close Juno looks, there is always more detail, more complexity. And the storms are changing, slowly. Tracking the cyclones over 8 years of observations reveals that they are drifting toward the poles. The motion is gradual, less than 1 degree of latitude per year. But it is systematic. All the cyclones are moving poleward. As they approach the rotational axis, they begin clustering more tightly. The geometric patterns compress. The storms interact more strongly. What happens when they reach the pole? No one knows. The timescales are too long to observe directly. If the drift continues at the current rate, the storms will collide with the central polar cyclone in decades or centuries. They might merge into a single enormous vortex spanning the entire polar region. Or they might find a new equilibrium configuration even closer to the pole. Or the pattern might become unstable and break down entirely, scattering the storms across higher latitudes. The polar cyclone arrays are not the only atmospheric mysteries Juno discovered. Radio occultation experiments conducted during the spacecraft's 53rd orbit in February 2023 provided the first direct measurements of Jupiter's stratospheric temperature structure at the poles. The technique involves transmitting a radio signal from Earth to Juno and back. The signal passes through Jupiter's atmosphere twice. As the radio waves travel through layers of gas at different temperatures and densities, they bend. By precisely measuring how much the signal refracts, scientists can determine the atmospheric temperature profile at different altitudes. 26 radio occultation soundings have been completed. The results revealed that Jupiter's north polar stratosphere is 11 degrees Celsius cooler than the surrounding regions. At the same latitude, the stratosphere is the atmospheric layer above the troposphere, where clouds form. On Earth, the stratosphere is where the ozone layer exists. On Jupiter, the stratosphere contains haze particles created by photochemical reactions driven by ultraviolet light from the sun. The cold polar stratosphere is encircled by winds exceeding 160 kilometers per hour. This creates a polar vortex similar to the stratospheric vortex that forms over Earth's poles during winter. The difference is that Jupiter's polar vortex is permanent. It does not form seasonally. It persists year-round because Jupiter has essentially no axial tilt. The poles never experience summer or winter. The discovery of a cold stratospheric cap affects models of Jupiter's global circulation. The temperature gradient between the pole and lower latitudes drives atmospheric motion. The winds encircling the polar region act as a barrier that prevents mixing between polar air and mid-latitude air. This isolation might explain why. The polar cyclone arrays remain confined to such a narrow latitude band. The atmospheric circulation at the poles is decoupled from the rest of the planet. But the stratospheric temperature measurements also revealed something unexpected. The temperature variations do not match predictions from models that assume Jupiter's atmosphere is in radiative convective equilibrium. The polar stratosphere is colder than it should be based on the balance between absorbed sunlight and emitted infrared radiation. Something is removing heat from the polar stratosphere more efficiently than radiation alone. One possibility involves gravity waves. These are not gravitational waves in the relativistic sense. Atmospheric gravity waves are oscillations in gas density and pressure that propagate vertically through the atmosphere. On Earth, gravity waves are generated by airflow over mountains or by convective storms. The waves carry energy and momentum upward. When they break in the stratosphere, they deposit energy and alter wind patterns. On Jupiter, convective storms in the troposphere might generate gravity waves that propagate into the stratosphere. If these waves break near the poles, they could accelerate winds and transport heat away from the polar region. This would explain the cold stratosphere and the strong circumpolar jet. But detecting gravity waves on Jupiter is extremely difficult. The signatures are subtle. Juno's instruments are not designed to measure the small-scale atmospheric fluctuations that characterize gravity wave activity. Another possibility involves interaction between the atmosphere and the magnetosphere. Charged particles trapped in Jupiter's magnetic field spiral along field lines and precipitate into the atmosphere near the magnetic poles. These particles deposit enormous amounts of energy, driving the permanent auroras. But some of that energy must also heat the atmosphere. The question is where that heat goes. If auroral heating occurs primarily in the thermosphere, the uppermost atmospheric layer, the energy might be transported downward through atmospheric circulation. But if the heating is confined to altitudes above the stratosphere, it might create a temperature inversion that prevents heat from reaching the lower atmosphere. This could create a cold stratospheric layer sandwiched between a hot thermosphere above and a warmer troposphere below. The atmospheric dynamics at Jupiter's poles are more complex than anyone anticipated. The cyclone arrays, the cold stratosphere, the permanent auroras, the interaction with the magnetosphere. These phenomena are interconnected. They influence each other through mechanisms that are only beginning to be understood. And they are unique to Jupiter. No other planet in the solar system displays this combination of features. Saturn has a single hexagonal jet stream pattern at its north pole. But no cyclone array. Uranus and Neptune have not been observed in sufficient detail to know if polar cyclones exist. Earth's poles have winter polar vortices but no permanent storm arrays. Jupiter's polar regions are laboratories for studying atmospheric physics under conditions that cannot be replicated on Earth or in any laboratory. The combination of rapid rotation, internal heat flux, strong magnetic fields, and hydrogen atmosphere creates dynamics that push fluid mechanics into regimes where intuition fails. The geometric arrays of cyclones are a reminder that we do not understand atmospheric circulation as well as we thought. The patterns emerge spontaneously from the equations of fluid dynamics. They self-organize without external forcing. They persist without obvious stability mechanisms. They are order emerging from chaos, structure arising from turbulence. And they have been spinning since before humans existed, before mammals evolved, before dinosaurs walked Earth. The polar cyclones might have formed when Jupiter was young. 4 billion years ago, they might be the oldest storms in the solar system. Eternal hurricanes locked to a spinning giant that will outlive the sun. "422,000 kilometers from Jupiter's center, a moon is being destroyed, Io. Slightly larger than Earth's moon, a world that should be cold, dead, cratered. Instead, its surface glows with lava. 400 active volcanoes erupt continuously. Plumes of sulfur dioxide gas shoot 500 kilometers into space. The surface is painted yellow, orange, red, and black. Sulfur in every oxidation state. Fresh lava flows covering impact craters before they can form. Io is the most volcanically active body in the solar system. And it is getting worse. On December 27, 2024, Juno flew past Io at a distance of 74,400 kilometers. The spacecraft's Jovian infrared auroral mapper locked onto the moon's southern hemisphere. The infrared detector measured thermal radiation, heat, the signature of volcanic activity. What JIRAM recorded should not have been possible. A hotspot larger than Lake Superior. Temperatures exceeding 1,700 degrees Celsius. Thermal emissions so intense it saturated the detector. The sensor could not measure the peak brightness. The signal maxed out. Engineers had to extrapolate the true temperature from surrounding pixels that were not saturated. Their calculations revealed an eruption releasing energy 6 times greater than all of Earth's power plants combined. A single volcanic vent outputting approximately 100,000 megawatts of thermal power. The eruption was still active when Juno returned on March 2, 2025. 2 months later, still vomiting lava, still glowing in infrared. Scientists expect it to remain active during Juno's next flyby on May 6th. This is not a brief volcanic episode. This is sustained eruption on a scale that has never been observed anywhere in the solar system. But the eruption itself was not the most disturbing discovery. Juno carries a microwave radiometer designed to peer beneath Jupiter's clouds. The MWR instrument measures microwave wavelength radiation emitted by warm objects. Microwaves can penetrate cloud layers. They can also penetrate solid surfaces. By measuring the intensity and frequency of microwave radiation, scientists can determine temperature at depth. The instrument was never intended for observing moons. But during Io flybys, the Juno team pointed the MWR at the volcanic world to see what it would detect. The results were shocking. Beneath Io's cooled surface crust lies still warm magma. Not solid rock, not frozen lava, liquid magma that is not solidified. The microwave data combined with infrared observations revealed subsurface temperatures consistent with molten rock at depths of several kilometers. Io has a magma ocean beneath its crust, an ocean of liquid rock, constantly churned, never allowed to freeze. Heated from within by tidal forces so intense they turn solid matter into fluid. Shannon Brown, a Juno scientist at NASA's Jet Propulsion Laboratory, described the finding bluntly. At every latitude and longitude observed, there were cooling lava flows, not scattered volcanic vents, not isolated hotspots. Everywhere. The entire moon is geologically active. This should not be possible. Volcanic activity requires heat. On Earth, volcanism is driven by radioactive decay in the mantle and by residual heat from planetary formation 4.5 billion years ago. Large rocky planets like Earth and Venus can retain heat for billions of years because their volume-to-surface area ratio is favorable. Small bodies cool rapidly. Earth's moon is geologically dead. Mars is mostly inactive. Even large moons like Ganymede and Callisto froze solid billions of years ago. Their surfaces are ancient, cratered, dead. Io should be frozen too. Its radius is only 1,821 kilometers, smaller than Earth's moon. A body this small should have lost its internal heat within the first billion years of the solar system's history. Any volcanism should have ceased long ago. The surface should be cold, cratered, geologically inert. Instead, Io is the most volcanically active world known to science, and the source of that activity is not radioactive decay. It is tidal heating. Jupiter's gravity pulls on Io with enormous force, but Io's orbit is not circular. It is slightly elliptical. As the moon swings closer to Jupiter and then farther away during each orbit, the gravitational force varies. When Io is near periaps, closest approach, Jupiter's gravity pulls harder. When Io is near apoaps, farthest point, the pull weakens. This varying gravitational force deforms Io. The moon's interior flexes, stretches, compresses. Like squeezing a rubber ball repeatedly, the deformation generates friction. Friction generates heat. The effect is called tidal heating. It is the same mechanism that causes Earth's tides. But on Io, the magnitude is incomprehensible. Jupiter's gravitational pull is 1,000 times stronger than the moon's pull on Earth. Io is squeezed and stretched by 600 meters twice per orbit. 600 meters of vertical displacement every 42.5 hours. The interior is kneaded like dough. Rock melts, magma rises, volcanoes erupt. But tidal heating alone is not sufficient to explain Io's extreme volcanism. If Io were the only moon orbiting Jupiter, tidal forces would quickly circularize its orbit. The moon would settle into a circular path where the gravitational force remained constant. Tidal heating would cease. Io would freeze. The reason Io's orbit remains elliptical is Europa. Europa orbits Jupiter at 671,000 kilometers. Exactly twice Io's orbital distance. This creates a 2-to-1 orbital resonance. For every 1 orbit Europa completes, Io completes exactly 2. Every time Io catches up to Europa, Europa's gravity tugs on Io. The repeated gravitational kicks prevent Io's orbit from becoming circular. They maintain the eccentricity, they sustain the tidal heating, they keep Io molten. Ganymede is also involved. Ganymede orbits at 1,070,000 kilometers, 4 times Io's distance. Ganymede, Europa, and Io are locked in a 3-body resonance. The orbital periods maintain exact integer ratios. The resonance is stable. It has persisted for billions of years, and it has sentenced Io to eternal geological torment. The tidal heating generates between 60 and 100 trillion watts of power inside Io. For comparison, Earth's total geothermal heat flux is approximately 47 trillion watts, Io, with only 1/40th of Earth's volume. Produces more than twice the geothermal heat. The heat flux per unit surface area is 50 times greater than Earth's most active volcanic regions. The Moon is essentially being cooked from the inside, but the distribution of volcanic activity on Io is not uniform. Some regions are far more active than others. The December 2024 eruption occurred near Io's South Pole. This region has historically been one of the most volcanically active zones on the Moon. Galileo spacecraft observations in the late 1990s revealed numerous hotspots in the southern hemisphere. Juno's observations confirm that the activity has not diminished. If anything, it has intensified. JunoCam visible light images captured in 2024 show significant surface changes near Io's South Pole compared to images from earlier flybys. Fresh lava flows cover regions that were previously dark. Bright deposits surround volcanic vents where sulfur dioxide frost has been ejected and settled back to the surface. The landscape is being resurfaced continuously. Any impact crater that forms is quickly buried by new lava. The surface age of Io is estimated at less than 1 million years. In geological terms, that is instantaneous. The volcanic plumes are visible even from Earth-based telescopes. When Io passes in front of Jupiter's disk, observers can see plumes silhouetted against the bright planet. Some plumes reach altitudes of 500 kilometers. The ejected material escapes Io's weak gravity. Sulfur and oxygen atoms are ionized by impacts with charged particles in Jupiter's magnetosphere. The ions get swept up by Jupiter's rotating magnetic field and form the Io plasma torus, a donut-shaped ring of electrically charged gas encircling Jupiter at Io's orbital radius. The plasma torus is one of the most intense sources of radio emission in the solar system. Jupiter's radio waves are strongly modulated by Io's position. When Io, Jupiter, and Earth align in specific geometric configurations, the radio intensity increases dramatically. This phenomenon is called Io-DAM, Io-controlled decametric radiation. Earth-based radio telescopes detected Io-DAM in the 1960s, decades before anyone understood that Io was volcanic. The radio emissions were the first clue that something extraordinary was happening on this small moon. The plasma torus also creates auroral emissions at Jupiter's poles. Electrical currents flow between Io and Jupiter along magnetic field lines. These currents carry millions of amperes of electrical charge. When the currents reach Jupiter's ionosphere, they generate localized auroral brightening called the Io footprint. Observers using the Hubble Space Telescope have imaged the Io footprint as a bright spot near Jupiter's pole that tracks Io's orbital motion. The footprint is connected to Io by a glowing column of plasma called the Io flux tube. The flux tube is a direct electrical connection between a moon and its planet. Nothing like this exists anywhere else in the solar system. Io's volcanism is destroying the moon, slowly, over geological time. Sulfur dioxide gas erupts from volcanic vents at velocities exceeding Io's escape velocity of 2.5 kilometers per second. The gas escapes into space, lost forever. Juno scientists estimate that Io loses approximately 1 ton of material per second to space. That does not sound like much. But over billions of years, the mass loss is significant. Io is evaporating. The evaporation rate might have been higher in the past when the tidal heating was more intense. Models of the orbital resonance evolution suggest that Io has been losing mass since the resonance formed billions of years ago. Some researchers estimate that Io might have lost 10 to 20% of its original mass. If true, Io was once substantially larger than it is today. A bigger moon with more gravity, more atmosphere, different geology. The Io we see now is a remnant, a wounded world bleeding material into space. But Io's mass loss feeds Jupiter's magnetosphere. The sulfur and oxygen atoms ejected from Io's volcanoes provide the raw material for the plasma torus. The torus provides the charged particles for Jupiter's auroras. The auroras generate the radio emissions. The radio emissions propagate across the solar system. The entire system is interconnected. Io's geological death powers Jupiter's electromagnetic life. The subsurface magma ocean Juno discovered adds a new dimension to understanding Io's interior structure. Previous models assumed that Io's volcanism was powered by pockets of magma rising from a partially molten mantle. Hot magma would ascend through cracks and conduits to reach the surface. The eruptions would be episodic, localized. But if a continuous layer of molten rock exists beneath the entire crust, the dynamics change completely. A magma ocean implies that Io's interior temperature exceeds the melting point of silicate rock throughout a thick shell surrounding the moon's core. The magma ocean might extend from 50 to 100 kilometers depth, all the way down to several hundred kilometers. This represents a substantial fraction of Io's interior. The heat required to maintain a magma ocean of this size is staggering. Tidal heating must be operating at the extreme upper end of theoretical predictions. The existence of a magma ocean also explains why Io's volcanism is so widespread. Magma does not need to rise from great depths through narrow conduits. It is already present just beneath the surface everywhere. Any weakness in the crust, any crack or fault, becomes a potential volcanic vent. Pressure from below forces magma upward. The result is the 400 active volcanoes distributed across Io's surface. The magma ocean also affects Io's response to tidal forces. A partially molten interior deforms more easily than solid rock. The tidal bulge can be larger. The energy dissipation more efficient. This creates a feedback mechanism. More melting leads to more efficient tidal heating. More heating creates more melting. The system can enter a runaway state where the moon becomes progressively more molten over time. Some models suggest that Io might be transitioning toward complete melting. The tidal heating rate might be increasing as the orbital resonance continues to evolve. If the heating rate exceeds the rate at which Io can radiate energy into space, the interior temperature will rise. More rock will melt. The magma ocean will thicken. Eventually, Io's entire mantle might become liquid. The moon would consist of a thin solid crust floating on an ocean of molten rock surrounding a small metallic core. But the process might be self-limiting. If the interior becomes too molten, the crust might become unstable. Large-scale overturn events could occur, where sections of crust founder and sink into the magma. New crust would form from solidified magma at the surface. This type of catastrophic resurfacing might have happened multiple times in Io's history. It might explain why the surface shows no ancient terrains. Everything old has been recycled. Io is a laboratory for understanding volcanism under extreme conditions. The lava compositions are different from terrestrial lava. Spectroscopic observations suggest that Io's lavas are rich in magnesium and silica. They might be ultramafic, similar to komatiite lavas that erupted on Earth. Billions of years ago, when the planet was hotter, the eruption temperatures exceed 1,700 degrees Celsius, hotter than modern terrestrial lavas. Hotter than anything currently active on Earth. The volcanic plumes contain sulfur dioxide, but also elemental sulfur, sodium chloride, potassium chloride. These compounds evaporate from lava at high temperatures and condense as frost on the surface. The multicolored terrain results from sulfur compounds in different oxidation states. Yellow sulfur, red sulfur, black sulfur compounds, white sulfur dioxide frost. The surface is a chemical palette painted by volcanic gases, and beneath it all, an ocean of magma churns. Never resting, never cooling, fed by gravitational torment that will continue as long as the orbital resonance persists. As long as Europa and Ganymede continue their gravitational dance. As long as Jupiter's gravity crushes Io with each orbit. The moon is dying. But it will take billions of years. And until then, Io will remain the most volcanically active world in the solar system. A hell moon orbiting a giant planet. A world where the ground glows with heat. Where lava flows like water. Where the sky rains sulfur. Where tidal forces turn solid rock into liquid, where geology operates at a pace that makes Earth's volcanism look glacial. Io is Jupiter's sacrifice, the price paid for Jupiter's magnetic splendor, the fuel for its auroras, the source of its radio voice, a moon being torn apart so that its parent planet can shine. "671,000 kilometers from Jupiter, beneath 15 kilometers of ice, an ocean exists that might harbor life. Europa. The smallest of Jupiter's 4 large Galilean moons. A world covered entirely by water ice. The surface is white, smooth, crisscrossed by fractures and ridges. No mountains, no impact craters. The youngest surface in the solar system except for Io. And beneath that frozen shell, more liquid water than exists in all of Earth's oceans combined. Scientists have suspected Europa's ocean since the 1990s. The Galileo spacecraft detected variations in Jupiter's magnetic field when Europa passed nearby. The variations indicated the presence of an electrically conductive layer beneath Europa's surface. Salt water conducts electricity. Ice does not. The magnetic signature proved that liquid water existed somewhere inside Europa. But magnetic measurements could not reveal the ocean's depth, its thickness, its chemistry, whether it touches the rocky seafloor or remains trapped between layers of ice. Juno provided new evidence. On September 29, 2022, Juno flew within 352 kilometers of Europa's surface, the closest any spacecraft had approached. The Moon since Galileo's final flyby in 2000. Juno's Stellar Reference Unit, a camera designed to track stars for navigation, captured the highest resolution images of Europa ever obtained. The images revealed terrain that confirmed the ocean's existence and suggested it is far more accessible than anyone predicted. The surface is chaos terrain. Blocks of ice broken and refrozen. Ridges tens of kilometers long and hundreds of meters high. Double ridges running parallel with valleys between them. Regions where the ice has fractured into plates that have rotated and shifted like ice flows on a polar sea. The geology is recent, active, ongoing. Near Europa's south polar region, Juno imaged an area nicknamed the Platypus because of its jumbled, irregular appearance. The Platypus region shows dark stains on the surface, material that is not ice. Spectroscopic observations suggest the dark material contains salts, sodium chloride, magnesium sulfate, compounds that exist in seawater on Earth. The salts appear to have erupted from below and frozen on the surface. If true, they provide direct samples of Europa's ocean chemistry without requiring drilling through 15 kilometers of ice. But the most significant discovery came from analyzing the ice shell structure itself. Europa's icy crust is not a static frozen shell. It moves. The ice behaves like Earth's tectonic plates. Sections of crust fracture and separate. New ice forms in the gaps. Old crust subducts, sinking back into the warmer ice below or perhaps into the ocean itself. This process is called ice tectonics. It requires heat from below. It requires a liquid layer that allows the ice to move. It confirms that Europa's ocean is in direct contact with the underside of the ice shell. The implications are staggering. On Earth, the ocean and atmosphere exchange material constantly. Gases dissolve in seawater. Seawater evaporates into the atmosphere. Nutrients from the ocean surface sink to the deep sea. Upwelling brings deep water back to the surface. This circulation is essential for life. It transports oxygen. It distributes nutrients. It prevents the ocean from stratifying into dead layers. Europa's ice tectonics might serve the same function. If the ice shell is mobile, material from the surface can be transported downward into the ocean, and material from the ocean can rise to the surface. This creates a pathway for chemical exchange. Surface ice is bombarded by Jupiter's radiation. The radiation breaks water molecules into hydrogen and oxygen. The oxygen remains trapped in the ice. If that oxygenated ice subducts into the ocean, it delivers oxygen to the subsurface sea. Life requires energy. On Earth's surface, sunlight provides energy for photosynthesis. Plants convert light into chemical energy. Animals eat plants. The food chain is powered by the sun. But Europa's ocean is buried beneath kilometers of ice. No sunlight penetrates. Any life in Europa's ocean must obtain energy through other means. Hydrothermal vents. On Earth's seafloor, volcanic vents spew superheated water rich in dissolved minerals: hydrogen sulfide, methane, iron, manganese. Microorganisms cluster around these vents. They feed on chemical energy released when vent fluids mix with seawater. They do not need sunlight. They do not need oxygen. They thrive in complete darkness using chemosynthesis rather than photosynthesis. These ecosystems are isolated from the surface biosphere. They could survive even if Earth's surface became uninhabitable. Europa might have hydrothermal vents. The Moon has a rocky core beneath its ocean. Tidal heating from Jupiter might keep that core partially molten. If volcanic activity occurs on the seafloor, hydrothermal systems could exist. Minerals would dissolve in the hot water. The water would rise through cracks in the seafloor and mix with the cold ocean. Chemical reactions would release energy. Microorganisms could harvest that energy. An entire ecosystem could exist independent of sunlight. But there is another source of chemical energy, one that does not require volcanism: serpentinization. When seawater reacts with certain types of rock, particularly minerals rich in iron and magnesium, chemical reactions occur that produce hydrogen gas and heat. This process is called serpentinization. It occurs on Earth wherever seawater infiltrates the oceanic crust. The hydrogen produced by serpentinization can react with carbon dioxide to form methane. These reactions release energy. Microorganisms on Earth use this energy. They are found in environments where serpentinization occurs. A 2016 NASA study concluded that Europa's ocean could produce hydrogen and oxygen through serpentinization and radiation processing at levels comparable to Earth's oceans. Even without volcanic activity, Europa might have sufficient chemical energy to support a biosphere. The study was based on modeling the chemistry of water-rock interactions on Europa's seafloor and the effects of radiation on surface ice. The ocean itself is likely salty, chloride-rich, similar to Earth's seawater. This conclusion comes from Hubble Space Telescope observations that detected sodium chloride on Europa's surface. Table salt, the same compound that makes Earth's ocean salty. The presence of chloride suggests that Europa's ocean has been in contact with rock long enough for minerals to dissolve. The water has leached elements from the seafloor. The chemistry has evolved. The ocean is not pure water. It is a mineral-rich brine. Mohit Melwani Daswani, a planetary scientist at NASA's Jet Propulsion Laboratory, led research in 2020 that modeled Europa's ocean chemistry over geological time. The study found that the ocean was likely mildly acidic when it first formed, with high concentrations of carbon dioxide and sulfate. But over hundreds of millions of years, the chemistry evolved. The ocean became more alkaline. Chloride concentrations increased. The water became more Earth-like, more habitable. Temperature is harder to determine. The ocean must be above 0 degrees Celsius to remain liquid. But how far above? Models suggest the temperature might range from 0 degrees near the ice-ocean interface to perhaps 4 degrees Celsius or higher near the seafloor, where geothermal heat is present, cold by human standards. But life on Earth thrives in cold water. The Arctic and Antarctic oceans are filled with organisms adapted to near-freezing temperatures. Cold is not an obstacle to biology. The ocean's depth is estimated between 60 and 150 kilometers, deeper than Earth's deepest ocean trench by a factor of 10. The pressure at the seafloor would be enormous, perhaps 100 to 200 times Earth's atmospheric pressure. But again, pressure is not an obstacle. Life on Earth exists in the Mariana Trench, where pressures exceed 1,000 times atmospheric pressure. Organisms adapted to high-pressure environments can survive and thrive. The volume of Europa's ocean is staggering. Estimates range from 2 to 3 times the volume of all Earth's oceans. For a moon only slightly smaller than Earth's moon, this is extraordinary. Europa contains more liquid water than Earth. It is an ocean world, a water planet masquerading as an icy moon. But does the ocean connect directly to space? Hubble Space Telescope observations in 2012 captured what appeared to be water vapor plumes erupting from Europa's surface. The images showed ultraviolet emissions consistent with water molecules backlit by Jupiter. The plumes extended 200 kilometers above the surface. They appeared to be erupting from the South Polar region. The discovery was revolutionary. If plumes exist, they provide a direct pathway to sample Europa's ocean. Without landing on the surface, a spacecraft could fly through the plume, collect water vapor, analyze the chemistry, search for organic molecules, perhaps even detect biological material. But the plumes vanished. Follow-up observations by Hubble in 2014 and 2016 detected similar features, but other observations saw nothing. The James Webb Space Telescope searched for plumes and found none. The plumes appear to be transient, episodic, not always active. Or perhaps they do not exist at all. Some researchers suggest the Hubble observations might have been misinterpreted. The ultraviolet emissions might result from other processes. Ice particles ejected by meteorite impacts reflected light from Europa's tenuous atmosphere. Instrumental artifacts. But in May 2018, researchers reanalyzing data from Galileo's Europa flyby in December 1997 found evidence that the spacecraft might have flown through a plume. Galileo passed within 206 kilometers of Europa's surface. During the flyby, instruments detected anomalies in the magnetic field and plasma wave data. The anomalies are consistent with passing through a localized column of water vapor. Erupting from the surface, the researchers did not recognize the signatures at the time. Only by comparing Galileo's data to Cassini observations of Enceladus's plumes did the pattern become clear. If the reanalysis is correct, it proves that Europa's plumes existed at least once. And if they existed in 1997, they might still exist today. The question is what triggers them. Are they continuous, seasonal, triggered by tidal stresses as Europa's orbit carries it closer to and farther from Jupiter? Do they erupt from the ocean, or from shallow subsurface lakes trapped within the ice shell? A November 2020 study suggested that the plumes might not originate from the deep ocean. The researchers proposed that pressurized pockets of water exist within Europa's ice shell. As the ice freezes and expands, pressure builds in these pockets. Eventually, the pressure exceeds the strength of the overlying ice. The ice fractures. Water erupts as a geyser. The process would be episodic, dependent on local ice conditions. Plumes from shallow sources would not provide direct samples of the ocean, but they would still contain water that originated from the ocean before becoming trapped in the ice. Either way, the plumes represent an opportunity. NASA's Europa Clipper mission, launched in October 2024, will search for them. The spacecraft carries instruments specifically designed to detect and analyze plume activity. The ultraviolet spectrograph will search for ultraviolet emissions from water vapor. The mass spectrometer for planetary exploration will sample gases if the spacecraft flies through a plume. The surface dust analyzer will collect ice particles ejected from Europa's surface by micrometeorite impacts or plume activity. Europa Clipper will not orbit Europa. The radiation environment is too intense. Prolonged exposure would destroy the spacecraft's electronics. Instead, Clipper will orbit Jupiter and conduct 49 close flybys of Europa. Each flyby will image different regions of the surface. Map the ice shell thickness using ice-penetrating radar. Measure the magnetic field to constrain ocean salinity and depth. Search for active geological features. Identify landing sites for future missions. The spacecraft will arrive at Jupiter in April 2030. 5.5 years of travel. Then 4 years of operations flying through the radiation belts. Dodging energetic particles that could cripple the spacecraft. Collecting data during brief flybys lasting only minutes before retreating to safer distances. It is a perilous mission, but the science return will be extraordinary. If Europa's ocean is habitable, Clipper will determine that. If plumes are active, Clipper will detect them. If organic molecules are present on the surface, Clipper will measure their composition. And if biosignatures exist, compounds that could only be produced by living organisms, Clipper might find them. But Europa Clipper is a habitability mission, not a life detection mission. The instruments are designed to assess whether conditions are suitable for life, not to confirm that life exists. Definitive proof of life would require landing on Europa's surface, drilling through the ice, accessing the ocean directly, or capturing pristine plume material and analyzing it in detail. Impossible during a high-speed flyby. Those missions are decades away. The technology to drill through 15 kilometers of ice in the extreme cold of Europa's surface does not yet exist. Concepts involve nuclear-powered thermal probes called cryobots that would melt their way through the ice. Upon reaching the ocean, a second probe called a hydrobot would be released to explore the subsurface sea. NASA's Scientific Exploration Subsurface Access Mechanism for Europa program is developing these technologies, but they will not be ready for deployment until the 2040s at the earliest. Until then, Europa remains tantalizingly out of reach, a world where an ocean exists, where chemical energy is available, where conditions might be suitable for life, but where no human instrument has tasted the water, no probe has explored the depths, no camera has seen what swims in the darkness. If life exists in Europa's ocean, it has been isolated for billions of years. It evolved independently from Earth. It would represent a second genesis, a second origin of life in our solar system. That discovery would be the most profound in human history. It would prove that life is not unique to Earth. That biology is a natural consequence of chemistry when conditions are right. That the universe might be filled with living worlds. But even if Europa is sterile, even if no organisms exist in its ocean, the moon remains extraordinary. It is a place where liquid water persists far from the sun, where geological activity continues billions of years after formation, where an entire world is hidden beneath ice, where an ocean exists that will outlast Earth's seas. Because when the sun becomes a red giant and evaporates Earth's oceans in 5 billion years, Europa will still have its subsurface sea, protected by kilometers of ice, shielded from the expanding sun, an oasis that will persist until Jupiter itself is destroyed. Europa is a promise, a possibility, a world that might answer the oldest question humanity has ever asked. Are we alone? "400 years ago, astronomers pointed primitive telescopes at Jupiter and saw a red oval on the planet's southern hemisphere. They assumed it was a temporary feature, a storm that would dissipate like terrestrial hurricanes. They were wrong. The Great Red Spot has been continuously observed since at least 1630. It might be far older. Ancient Chinese astronomers recorded observations of Jupiter, dating back 2,000 years. Some descriptions mention markings on the planet's disk. Those markings might have been the Great Red Spot. If so, the storm has been raging for millennia, spinning in place, never weakening, never dying. But the storm is changing. In 1879, when astronomers began systematic telescopic observations of Jupiter, the Great Red Spot measured 41,000 kilometers across. Its long axis, large enough to swallow 3 Earths side by side. By 1979, when Voyager 1 flew past Jupiter, the storm had shrunk to 23,000 kilometers. By 2017, Juno measured it at 16,000 kilometers. The spot is contracting. In the past 150 years, it has decreased in size by more than 60%. No one knows why. No one knows if it will stop shrinking or continue diminishing until it vanishes entirely. Computer models cannot predict the storm's future. The atmospheric dynamics are too complex. The interactions with surrounding jet streams too chaotic. The Great Red Spot might persist for another 1,000 years. Or it might collapse within a century. Scientists have no way to know. But Juno revealed something about the storm that no previous mission could detect: the storm's depth. On Earth, hurricanes are shallow features. They form in the troposphere, the lowest layer of the atmosphere where weather occurs. The troposphere extends from the surface to approximately 15 kilometers altitude. Above that is the stratosphere, where temperature increases with altitude and the air is stable. Hurricanes cannot penetrate into the stratosphere. They are confined to the lowest atmospheric layer. Typically, hurricane clouds extend no deeper than 10 to 15 kilometers. From top to bottom, Jupiter has no solid surface, no boundary where the atmosphere ends and the planet begins. The hydrogen gas smoothly transitions from low density at the cloud tops to higher density deeper down, eventually at thousands of kilometers depth. The gas becomes so compressed it behaves like a liquid. The pressure is so immense, the hydrogen atoms can no longer maintain their molecular bonds. The transition is gradual. There is no sharp interface. So how deep do Jupiter's storms extend? Juno answered this question using gravity measurements. When a massive storm spins in the atmosphere, it creates density variations. Rising air is less dense. Sinking air is more dense. These density differences create tiny variations in the gravitational field by measuring how Jupiter's gravity tugs on the spacecraft. During close flybys, scientists can detect these variations. The strength and pattern of the gravitational anomalies reveal the mass distribution. And mass distribution reveals depth. The Great Red Spot extends at least 320 kilometers beneath the visible cloud tops, possibly deeper. The measurements cannot resolve structures below approximately 350 kilometers because the gravity signal becomes too weak, but 320 kilometers is already extraordinary. That is 50 times deeper than Earth's deepest hurricanes. The Great Red Spot is not a surface storm. It is a three-dimensional vortex penetrating deep into Jupiter's interior. The storm contains more mass than previously calculated. The rotating winds are not just moving clouds, they are moving enormous volumes of dense gas. Extending hundreds of kilometers downward, the total energy contained in the storm is staggering. To maintain wind speeds exceeding 430 kilometers per hour. Over such a vast volume requires power input that dwarfs anything seen on Earth. But where does that energy come from? On Earth, hurricanes are powered by warm ocean water. Evaporation releases heat into the atmosphere. The heat drives convection. Air rises, pressure drops, more air flows inward. The Coriolis force from Earth's rotation causes the inflowing air to spin. The system organizes into a rotating vortex with an eye at the center. But Earth's hurricanes dissipate when they move over land or cold water. They lose their energy source. They die. Jupiter has no oceans, no land, no temperature gradient between different surface types. The energy driving the Great Red Spot must come from internal heat or from interactions with surrounding atmospheric flows, or both. Jupiter radiates more energy than it receives from the Sun. This internal heat drives convection throughout the atmosphere. Hot gas rises from the interior. Cool gas sinks. The planet's rapid rotation organizes these convection cells into the banded structure visible from Earth. Dark belts where gas is descending, bright zones where gas is rising. Between the belts and zones, powerful jet streams flow at hundreds of kilometers per hour. Eastward jets at some latitudes, westward jets at others. The jets are deep. Gravity measurements show they extend at least 3,000 kilometers into the interior. The Great Red Spot sits in a region where eastward and westward jets meet. The wind shear between opposing flows might help sustain the storm. Energy from the jets feeds the vortex. The vortex persists because the energy supply never stops. As long as Jupiter's interior continues to radiate heat, as long as convection continues, the jet streams will flow, and as long as the jets flow, the Great Red Spot can survive. But the storm is also violent. Lightning occurs within the Great Red Spot. Radio bursts detected by Juno indicate electrical discharge activity. On Earth, lightning forms when ice particles and water droplets collide within storm clouds. The collisions create charge separation. Positive charge accumulates in one region, negative charge in another. When the voltage difference becomes large enough, electrical breakdown occurs. A lightning bolt equalizes the charge. Jupiter's lightning works similarly, but with different materials. Instead of water, the clouds contain ammonia and ammonium hydrosulfide. These compounds freeze at temperatures found in Jupiter's upper atmosphere. Ice particles form. They collide. Charge separates. Lightning strikes. Juno's microwave radiometer detected lightning at depths where water clouds should exist, 5 to 7 bars of pressure, approximately 100 kilometers beneath the visible ammonia clouds. The lightning storms on Jupiter are continuous. Thousands of strikes occur every hour. The radio emissions are detectable from Earth. Jupiter's lightning is more powerful than terrestrial lightning. Individual bolts release energies exceeding those of Earth's strongest lightning by factors of 10 or more. The Great Red Spot is not just a windstorm, it is an electromagnetic maelstrom. But the Great Red Spot is not the only massive storm on Jupiter. The planet is covered with smaller anticyclonic vortices, white ovals, brown barges, chaotic regions where multiple storms interact. Some of these features have been tracked for decades. Others appear and disappear on timescales of months to years. The atmosphere is in constant turmoil. One particularly interesting feature is the South Equatorial Belt disturbance. This is a region where the normally dark brown belt fades to white over a period of months before returning to its original color. The fading occurs irregularly, sometimes once per decade, sometimes more frequently. No one knows what causes the color change. Theories involve changes in cloud particle size or chemical composition, but the mechanism remains unknown. The colors themselves are mysterious. Jupiter's clouds should be white. Ammonia ice is white. Water ice is white. Yet Jupiter displays shades of red, brown, orange, and yellow. Something is creating colored compounds in the atmosphere. Candidates include sulfur compounds, phosphorus compounds, or complex organic molecules called tholins, created by ultraviolet radiation breaking apart methane and ammonia molecules. Laboratory experiments have synthesized reddish-brown compounds by irradiating ammonia and methane mixtures. But no one has definitively identified the chromophores responsible for Jupiter's colors. The vertical structure of Jupiter's atmosphere adds another layer of complexity. The topmost layer is a haze created by photochemical reactions. Below that, ammonia ice clouds form at pressures around 0.5 bars. Deeper, at 2 to 3 bars of pressure, ammonium hydrosulfide clouds exist. Deeper still, at 5 to 7 bars, water ice clouds should form. But Juno's microwave radiometer revealed that water is not uniformly distributed. Some regions have more water vapor than others. The water concentration varies by factors of 2 to 3 across different latitudes. This is unexpected. If Jupiter formed by capturing gas from the solar nebula, the water abundance should reflect the primordial composition of the Sun. Measurements of the Sun's composition show a specific oxygen-to-hydrogen ratio. Jupiter's water abundance should match that ratio, but it does not. In some regions, Jupiter is water-depleted. In others, water-enriched. This suggests complex atmospheric dynamics are transporting water vapor between different altitude levels and latitudes. Or it suggests that Jupiter's formation history was more complicated than simple gas capture. One hypothesis involves Jupiter's migration through the early solar system. Theoretical models suggest that Jupiter did not form at its current distance from the Sun. The planet might have formed farther out where more water ice was available. After forming, gravitational interactions with the protoplanetary disk caused Jupiter to migrate inward. The migration brought Jupiter to its present location. If this occurred, Jupiter might have accumulated material from different regions of the solar system, with different chemical compositions. The varying water abundance could reflect that heterogeneous accretion. But Juno discovered another atmospheric anomaly that no one predicted: ammonia, the compound that creates Jupiter's white zones and clouds. Juno's microwave radiometer can measure ammonia concentration at different depths. The data revealed that ammonia is not uniformly mixed throughout the atmosphere. At the equator, ammonia is depleted at certain altitudes. At higher latitudes, ammonia is more abundant. The distribution is complex, three-dimensional, and it is changing over time. The ammonia variations appear to be connected to Jupiter's jet streams. The powerful east-west winds transport ammonia from equatorial regions toward the poles, but the mechanism is not simple advection, gas being blown by wind. Instead, the ammonia appears to be transported vertically before being carried horizontally. Ammonia-rich gas rises from deep in the atmosphere at certain latitudes. The gas flows horizontally along jet streams, then it descends at other latitudes. The result is a global circulation pattern that redistributes ammonia in ways that atmospheric models did not predict. This has implications for understanding gas giant atmospheres around other stars. Thousands of exoplanets have been discovered. Many are gas giants similar to Jupiter. Astronomers measure the atmospheric composition of these exoplanets using spectroscopy. When an exoplanet transits in front of its star, starlight passes through the planet's atmosphere. Different molecules absorb light at specific wavelengths. By measuring which wavelengths are absorbed, scientists can determine atmospheric composition. But if Jupiter's atmosphere is not uniformly mixed, if ammonia and water vary significantly with latitude and altitude, then exoplanet observations might be sampling only specific regions of the atmosphere. The measured composition might not represent the global average. This could lead to incorrect conclusions about exoplanet formation and chemistry. Juno's discoveries at Jupiter provide crucial ground truth for interpreting observations of distant worlds. The Great Red Spot will eventually die. Whether in decades or millennia, the storm will dissipate, the winds will slow, the vortex will break apart, Jupiter's atmosphere will smooth over the region where the spot existed. Perhaps a new storm will form elsewhere, perhaps not. But for now, the Great Red Spot endures, a monument to atmospheric violence, a storm older than nations, a vortex that has outlasted empires and civilizations, a reminder that Jupiter's atmosphere operates on time scales and energy scales that dwarf anything terrestrial. And beneath it all, 320 kilometers down, the storm's roots reach into depths where pressure crushes gas into liquid, where temperature soars past 1,000 degrees Celsius, where the boundary between atmosphere and interior blurs into irrelevance. The Great Red Spot is not just a surface feature. It is a conduit connecting Jupiter's visible face to its hidden interior, a window into the planet's heart. Between Io's orbit and Jupiter's cloud tops lies a region of space that would kill a human in seconds. Not from heat, not from pressure, from radiation. Charged particles trapped in Jupiter's magnetic field spiral along field lines at velocities approaching the speed of light. Electrons, protons, heavy ions. They form belts of radiation encircling the planet like invisible death rings. The particle energies are so extreme they penetrate metal. They destroy electronics, they shred biological tissue at the molecular level. This is Jupiter's magnetosphere, the largest structure in the solar system, and the most lethal environment any spacecraft has ever encountered. The radiation belts extend from Jupiter's cloud tops outward to approximately 2 million kilometers. But the intensity is not uniform. The most dangerous region exists between Jupiter's surface and Io's orbit at 422,000 kilometers. Here, particle fluxes reach levels that exceed anything in Earth's vicinity by factors of 1 million or more. A human standing in this region unshielded would receive a lethal radiation dose in less than 1 second. Death would not be immediate. It would take hours for radiation sickness to kill, but the dose would be irreversible, fatal, guaranteed. Juno survives by avoiding the worst regions. The spacecraft's polar orbit carries it over Jupiter's north and south poles, threading between the most intense radiation belts concentrated near the equator. Even so, each close pass exposes Juno's electronics to cumulative damage. The spacecraft is encased in a titanium vault weighing 200 kilograms. The vault shields critical electronics from radiation. But shielding is not perfect. High-energy particles penetrate, slowly degrading components, creating errors in computer memory, damaging sensors. By Juno's 69th orbit in January 2025, radiation effects were becoming evident. The JunoCam visible light imager began showing signs of damage. During the spacecraft's 47th orbit, nearly all images became corrupted by radiation-induced errors. Engineers identified the problem as a damaged voltage regulator. They developed a workaround. By heating the camera to 25 degrees Celsius, a process called annealing, they could temporarily repair radiation damage at the atomic level. The technique works. Juno continues operating. But each orbit adds more damage. Eventually, annealing will no longer be effective. The camera will fail permanently. Other instruments are also deteriorating. The Stellar Reference Unit, designed to track stars for navigation, occasionally reports false detections. Cosmic rays striking the detector create signals that mimic stars. The spacecraft's computer must filter these phantom stars from real ones. The microwave radiometer shows increased noise in some frequency channels. The magnetometer remains functional, but has experienced occasional data dropouts. Juno is dying. Slowly. Radiation is killing it. The mission was originally planned to end in February 2018 after 37 orbits. NASA extended the mission to July 2021, then to September 2025. Each extension pushes Juno deeper into the radiation environment. Each orbit brings the spacecraft closer to catastrophic failure. The mission will end not because of fuel depletion, but because radiation will destroy too many critical systems. For the spacecraft to continue operating. The radiation itself comes from multiple sources. Jupiter's magnetic field traps charged particles from the solar wind. But most particles originate from Io. The volcanic moon ejects sulfur and oxygen ions into space. Jupiter's rotating magnetic field ionizes these atoms and accelerates them to high velocities. The ions spiral along magnetic field lines, bouncing between northern and southern hemispheres. They gain energy with each bounce. Eventually, they reach relativistic speeds. This acceleration mechanism is similar to the process that creates Earth's Van Allen radiation belts. But Jupiter's belts are far more intense. The particle energies are higher. The fluxes are greater. The spatial extent is enormous. If Jupiter's magnetosphere were visible to human eyes, it would appear larger than the full moon from Earth, despite being over 600 million kilometers away. The radiation affects not just spacecraft, but also Jupiter's moons. Ganymede orbits at 1,070,000 kilometers, well within the radiation belts. The moon's surface is continuously bombarded by high-energy particles. The radiation breaks chemical bonds in surface ice. It creates hydrogen peroxide and molecular oxygen. It darkens the ice over time. Ganymede has its own magnetic field, the only moon in the solar system with an intrinsic magnetic field. This field creates a mini magnetosphere that deflects some of Jupiter's radiation. But the shielding is incomplete. Ganymede's surface still receives intense radiation doses. Europa orbits closer at 671,000 kilometers. The radiation there is even more extreme. Europa lacks a magnetic field. It has no protection except its ice shell. The surface receives radiation doses of approximately 500 to 5,000 rads per day. For comparison, a lethal dose for humans is approximately 400 to 500 rads total. Europa's surface receives that much every few hours. Any organic molecules on the surface are destroyed, sterilized, broken apart into simple compounds. This has profound implications for searching for life on Europa. If life exists in the subsurface ocean, it is protected by 15 kilometers of ice. But any biological material that reaches the surface is annihilated by radiation. This means surface sampling missions cannot detect biosignatures directly. The radiation would have destroyed them. Only subsurface samples, either from plumes or from drilling through the ice, could preserve organic compounds long enough for detection. Callisto orbits at 1,882,000 kilometers, beyond the most intense radiation. The particle flux at Callisto's distance is roughly 1,000 times lower than at Europa. Callisto's surface is ancient, heavily cratered, geologically dead. But it is also the safest location in the Jupiter system for a future human outpost. If astronauts ever travel to Jupiter, they will likely establish bases on Callisto, where radiation exposure is survivable with reasonable shielding. The radiation belts are not static. They pulse with Jupiter's rotation. They respond to solar wind pressure. When the sun releases a coronal mass ejection and the solar wind intensifies, Jupiter's magnetosphere compresses. The radiation belts shift inward. Particle fluxes increase. Spacecraft traversing the magnetosphere experience heightened radiation during these events. Juno's radiation monitoring instruments track these variations. The data helps engineers predict when radiation levels will peak and schedule sensitive operations during quieter periods. But even during quiet periods, the radiation environment is brutal. Measurements show that the radiation dose at Io's orbital distance exceeds 36 million rads per day. This is radiation intensity found nowhere else in the solar system, except near the sun's surface. Any electronics exposed to this flux would fail within hours. Any biological tissue would be reduced to chemical soup. The radiation also creates another phenomenon: synchrotron radiation. When relativistic electrons spiral along magnetic field lines, they emit electromagnetic radiation. This is the same process that occurs in particle accelerators on Earth. Scientists use synchrotron radiation for research because it produces intense X-rays and ultraviolet light. Jupiter's radiation belts generate synchrotron radiation naturally. The emissions are detectable from Earth using radio telescopes. They appear as a radio glow surrounding Jupiter at frequencies of 0.1 to 15 gigahertz. The synchrotron radiation provides information about the radiation belt structure. By measuring the intensity and spectrum of radio emissions, scientists can determine the energy distribution. Trapped electrons. The measurements reveal that Jupiter's radiation belts contain electrons with energies exceeding 100 million electron volts. These are particles moving at 99% of light speed or faster. When these particles strike matter, they penetrate deeply. They create secondary radiation through nuclear interactions. They are unstoppable by conventional shielding. This is why exploring Jupiter's inner magnetosphere is so challenging. Spacecraft cannot survive there for extended periods. The Galileo orbiter, which operated from 1995 to 2003, repeatedly passed through the radiation belts. During its moon flybys, by the end of the mission, radiation had caused multiple instrument failures. The spacecraft's camera stopped working, the tape recorder jammed. Thrusters became unreliable. Galileo's final act was a controlled dive into Jupiter's atmosphere to prevent contaminating Europa with Earth microbes. The spacecraft burned up on September 21, 2003. Juno will meet a similar fate. When the mission ends in September 2025, the spacecraft will be commanded to deorbit. It will plunge into Jupiter's atmosphere at over 200,000 kilometers per hour. Atmospheric friction will heat the spacecraft to thousands of degrees. Juno will vaporize. Its atoms will mix with Jupiter's hydrogen and helium. The spacecraft will become part of the planet it studied. This is necessary to protect Jupiter's moons. International planetary protection protocols require that spacecraft be disposed of in ways that prevent contaminating potentially habitable worlds. Europa might harbor life. Ganymede might have a subsurface ocean. These environments must not be polluted by Earth organisms. Even dead spacecraft could carry dormant microbes that might survive in space for decades or centuries. If Juno were left in orbit, it might eventually crash into one of Jupiter's moons. The collision could release terrestrial contamination. Deorbiting into Jupiter eliminates this risk. The planet's atmosphere sterilizes everything it touches. But before Juno dies, it continues transmitting data that no other spacecraft can obtain. The radiation measurements are scientifically valuable. They help researchers understand how planetary magnetospheres trap and accelerate particles. They provide ground truth for models of radiation belt dynamics. They reveal how magnetic fields interact with plasma on scales ranging from planetary to stellar. Jupiter is a laboratory for studying processes that occur throughout the universe. Pulsars operate on similar principles. These rapidly rotating neutron stars have magnetic fields billions of times stronger than Jupiter's. They trap charged particles and accelerate them to nearly light speed. The particles emit radio waves as they spiral along magnetic field lines. The radio emissions pulse with the star's rotation period. Jupiter is essentially a weak pulsar. It rotates rapidly. It has a strong magnetic field. It traps and accelerates particles. It emits radio waves. The physics is the same, only the scale differs. By studying Jupiter, scientists gain insights into pulsar behavior. They test theories of magnetohydrodynamics in extreme environments. They observe how magnetic fields channel plasma flows. They watch auroral acceleration in real time. Jupiter is accessible, observable, measurable. Pulsars are distant, unresolved. Theoretical. Jupiter provides the experimental data that pulsar studies lack. The radiation belts also affect space weather throughout the outer solar system. Jupiter's magnetosphere extends so far that it can influence spacecraft operating near Saturn. When NASA's Cassini orbiter was approaching Saturn in 2004, it detected bursts of energetic particles that appeared to originate from Jupiter. The particles had traveled over 1 billion kilometers through interplanetary space. They were part of Jupiter's radiation environment escaping the magnetosphere and propagating through the solar system. This has implications for future crewed missions to the outer solar system. Astronauts traveling to Jupiter or Saturn will encounter enhanced radiation levels even in interplanetary space. Mission planners must account for this. When designing spacecraft shielding and calculating radiation exposure limits. The journey to Jupiter takes 5 years using current propulsion technology. 5 years of cosmic ray exposure, plus additional exposure from Jupiter's magnetosphere during the mission. The cumulative radiation dose might exceed safe limits for humans, unless new technologies are developed. Active shielding using magnetic fields. Radiation-resistant electronics. Biological countermeasures that repair radiation damage faster than it accumulates. These technologies do not yet exist. They are theoretical, but they must be developed before humans can explore the outer solar system. Jupiter's radiation environment is a barrier, not just to spacecraft, but to human ambition. The planet is hostile. The magnetosphere is lethal. Any future exploration will require confronting the radiation challenge, solving it, or accepting that Jupiter will remain forever accessible only to robots, machines designed to die in the service of science. And die they do. Every spacecraft that has visited Jupiter has been damaged or destroyed by radiation. Pioneer 10 and 11, Voyager 1 and 2, Ulysses. Cassini during its flyby. Galileo, New Horizons during its gravity assist, and now Juno. All have been wounded by the planet's invisible violence. All have sacrificed their operational lifetimes to deliver data about a world that kills machines as efficiently as it would kill flesh. The radiation is a warning. Jupiter is not benign. It is not safe. It is a giant surrounded by a death zone millions of kilometers wide. And in September 2025, Juno will join the graveyard, another spacecraft consumed by the planet it tried to understand. Everything we thought we understood about how planets form is wrong. Jupiter's existence should not be possible. According to standard planetary formation theory, gas giants form through a process called core accretion. A rocky core, 10 to 15 times Earth's mass, assembles from collisions of smaller bodies in the protoplanetary disk. Once the core reaches sufficient mass, its gravity becomes strong enough to capture hydrogen and helium gas. From the surrounding nebula, the gas accumulates rapidly. Within a few million years, a gas giant is born. But there is a problem. The protoplanetary disk dissipates quickly. Observations of young stars show that gas-rich disks vanish within 3 to 5 million years. Solar radiation and stellar winds blow the gas away. The disk clears. No more material is available for planet formation. If Jupiter's core took longer than 5 million years to form, there would have been no gas left to capture. Jupiter could not exist. Yet Jupiter exists. And Juno revealed that its interior does not match the predictions of core accretion theory. The diluted core, the dissolved heavy elements, the asymmetric magnetic field, the complex atmospheric circulation. None of this fits neatly into existing models. One alternative is gravitational instability formation. Instead of slowly building a core and then capturing gas, the entire planet forms at once. A massive clump of gas in the protoplanetary disk becomes gravitationally unstable. It collapses directly into a gas giant without ever forming a rocky core first. This process is fast. It can occur within a few thousand years, fast enough to beat the disk dissipation timescale. But gravitational instability requires specific conditions. The disk must be massive enough, cold enough, extended enough, Computer simulations show that gravitational instability can form gas giants at large distances from the star, beyond 30 or 40 astronomical units. But Jupiter orbits at 5.2 astronomical units. The conditions for gravitational instability probably did not exist at Jupiter's current location, unless Jupiter did not form where it is now. Planetary migration is now recognized as a fundamental process in planetary system evolution. Planets do not remain at their birth locations. They migrate inward or outward through gravitational interactions with the protoplanetary disk or with other planets. Evidence for migration is everywhere. Hot Jupiters orbit their stars at distances of 0.05 astronomical units or less. These planets could not have formed that close to their stars. The temperatures would have been too high for gas to condense. They must have formed farther out and migrated inward. Jupiter likely migrated too. Theoretical models suggest that Jupiter formed beyond the snow line, the distance from the Sun where water ice could condense. This might have been at 8 or 10 astronomical units from the Sun, instead of Jupiter's current 5.2. At that distance, more solid material was available. The core could have formed faster. Once formed, interactions with the gas disk caused Jupiter to migrate inward. It spiraled toward the Sun, but before it could migrate too far, Saturn formed. The two planets became locked in a resonance that halted their inward migration, and may have even caused them to migrate outward slightly. This migration explains several features of the solar system. The asteroid belt between Mars and Jupiter contains less mass than it should. Something removed material from that region. Jupiter's migration could have scattered asteroids as it passed through. The inner solar system planets are relatively small. Earth is tiny compared to Jupiter. If Jupiter had migrated all the way to the inner solar system, it would have ejected or accreted the material that became the terrestrial planets. Earth might not exist. The migration hypothesis also explains Jupiter's composition. If the planet formed farther from the Sun, it would have accumulated more water ice and other volatiles. This matches observations. Jupiter is enriched in heavy elements compared to the Sun. The enrichment suggests the planet formed where solid material was more abundant. As Jupiter migrated inward, it swept up additional planetesimals. These collisions delivered even more heavy elements to the interior. But migration creates new problems. If Jupiter migrated significantly, it would have destabilized the orbits of other planets in the solar system. Mars might have been ejected. The asteroid belt should have been completely cleared. The outer solar system should look different than it does. Yet the solar system's architecture is relatively stable. The planets are where they are. The orbits are not chaotic. Something limited Jupiter's migration. The Nice model, named after the city in France where it was developed, proposes a solution. According to this model, the outer planets initially had orbits closer together than today. Jupiter, Saturn, Uranus, and Neptune were more compact. Over hundreds of millions of years, gravitational interactions with leftover planetesimals caused the planets to slowly migrate. Jupiter moved inward. Saturn moved outward. Eventually, Saturn crossed a critical orbital ratio with Jupiter. The two planets entered a 2-to-1 resonance. This triggered orbital instability. The instability scattered the remaining planetesimals throughout the solar system. Uranus and Neptune were thrown outward to their current positions. Planetesimals were flung into the inner solar system, creating the Late Heavy Bombardment that cratered the Moon and Earth 4 billion years ago. After the planetesimals were cleared, the planetary orbits stabilized into their current configuration. The Nice model explains many features of the solar system, but it requires extremely specific initial conditions. The planets must start in just the right orbital configuration. The timing of the resonance crossing must occur at exactly the right moment. The model works in computer simulations, but the parameter space where it works is narrow. Small changes to initial conditions produce completely different outcomes. Some runs eject planets entirely. Others send planets crashing into the Sun. This is the formation paradox. Jupiter exists, it has the mass and composition it has, it orbits where it orbits. Yet the formation pathway that led to this outcome appears statistically unlikely. We are either missing something fundamental about planetary formation physics. Or we live in a solar system that represents an unusual outcome from a stochastic process. Juno's discoveries deepen the paradox. The dissolved core suggests that Jupiter's interior has undergone significant evolution since formation. Core erosion might have been driven by a massive collision early in Jupiter's history. Theoretical work by Konstantin Batygin at Caltech and Fred Adams at the University of Michigan revealed that 4 billion years ago, Jupiter was twice its current radius. The planet was puffed up, bloated. Something caused it to contract. A collision with a planetary mass body could explain this. If a Mars-sized or Earth-sized object struck Jupiter when the planet was young, the impact energy would have heated the interior. The planet would have expanded temporarily. Over millions of years, it would cool and contract back down. But the collision would also deliver heavy elements, mix the interior, potentially start the core erosion process that led to the current diluted state. Evidence for such a collision comes from analyzing the orbits of Jupiter's small inner moons Amalthea and Thebe. These moons have slightly tilted orbits. The tilt can be used to reconstruct Jupiter's past rotational state and interior structure. The calculations indicate that ancient Jupiter had a magnetic field 50 times stronger than today. The stronger field implies a more vigorous dynamo, more rapid convection, higher internal temperatures, all consistent with a planet that had recently been heated by a massive impact. But proving a collision occurred is impossible. The event would have happened 4 billion years ago. No direct evidence remains. The impactor merged with Jupiter. Its material distributed throughout the interior. Only indirect clues survive in the current state of Jupiter's moons and magnetic field. The formation paradox extends beyond Jupiter. Every gas giant in the solar system presents puzzles. Saturn has a lower density than water. If you could find an ocean large enough, Saturn would float. This implies Saturn has an even higher proportion of hydrogen and helium than Jupiter. Yet Saturn orbits farther from the Sun where less gas should have been available during formation. Why is Saturn so gas-rich? Uranus and Neptune are ice giants rather than gas giants. They contain much more rock and ice relative to hydrogen and helium. Their atmospheres are thin. Their interiors are likely slushy mixtures of water, methane, and ammonia under high pressure. They orbit so far from the Sun that core accretion should have taken tens of millions of years, far longer than the protoplanetary disk lifetime. Yet they exist. Somehow they formed fast enough to capture at least some gas before the disk dissipated. And their magnetic fields are bizarre. Both Uranus and Neptune have magnetic fields tilted dramatically relative to their rotation axes. Uranus's magnetic field is tilted 59 degrees. Neptune's is tilted 47 degrees. Earth's magnetic field is tilted 11 degrees. Jupiter's is tilted 10 degrees. The ice giants are completely different. Their dynamos operate in ways that do not match the gas giants. The reason is unknown. The diversity of giant planets challenges formation theory. If all four formed through the same mechanism, why are they so different? If they formed through different mechanisms, what were those mechanisms, and why did each planet follow a different pathway? Exoplanet discoveries have made the paradox even more acute. Thousands of gas giants have been found orbiting other stars. Many are hot Jupiters orbiting extremely close to their stars. Many are super-Jupiters with masses 5 or 10 times Jupiter's mass. Many orbit in highly elliptical orbits. Many orbit in systems with multiple giant planets packed together more tightly than models predict is stable. The diversity of exoplanetary systems is staggering. No two systems are alike. Gas giants appear in configurations that were never predicted by pre-exoplanet theory. The models developed to explain our solar system do not work for most exoplanets. Either those models are incomplete, or our solar system is atypical. Juno's observations provide critical data for testing formation theories. The interior structure of Jupiter constrains how the planet evolved after formation. The atmospheric composition reveals what materials were available during formation. The magnetic field properties indicate the thermal state of the interior. These are ground truth measurements that can be compared to model predictions. But the measurements also reveal how much we still do not understand. Why is the core diluted? Why is the magnetic field asymmetric? Why is water distributed unevenly in the atmosphere? Why do the polar cyclone arrays exist? These are not minor details. They are fundamental features that formation models should predict but do not. The gap between theory and observation suggests that planetary formation is more complex than current models capture. There are processes we have not identified. Physics we have not included. Initial conditions we have not constrained. Jupiter is not just a gas giant. It is a puzzle with pieces that do not fit together cleanly. Using the tools we have. And if we cannot fully explain Jupiter, a planet in our own solar system that we can observe in detail, how can we hope to understand exoplanets that are mere points of light in distant spectra? The answer is that we cannot. Not yet. Understanding planetary formation requires more data, more observations, better models. Juno provides some of that data. But Juno observes only one planet at one moment in its evolution. To understand formation, we need to observe planets at different stages, different masses, different compositions, different orbital configurations. That requires more missions, more spacecraft, more decades of exploration. The Europa Clipper will reveal Europa's ocean. The European Space Agency's JUICE mission will study Ganymede. Future missions might explore Uranus and Neptune. Each mission adds pieces to the puzzle. Each discovery constrains formation theories. Slowly, over generations, the picture will clarify. But for now, Jupiter remains enigmatic, a planet that should not exist, or at least should not exist in the configuration it does. A world that challenges our models and exposes the limits of our understanding, a giant that has been visible in Earth's sky for all of human history, but whose origin story remains frustratingly incomplete. The formation paradox is a humbling reminder. We have been studying Jupiter for 400 years. We have sent 9 spacecraft to observe it. We have built computer models that simulate its evolution over billions of years. We have written tens of thousands of scientific papers analyzing its properties, and yet we still cannot explain with certainty how it came to be. Jupiter is 590 million kilometers away, visible to the naked eye, observable from backyard telescopes, and still, fundamentally, a mystery. You have descended into Jupiter, through the clouds, through the hydrogen ocean, into the metallic abyss where electrons flow like water and magnetic fields tear reality apart. You have witnessed volcanic moons being tortured by gravity. You have seen storms older than civilizations. You have watched radiation belts that would sterilize worlds. You have explored an ocean beneath ice that might harbor alien biology. And now you understand the truth. Jupiter is not a planet, it is a mechanism. A dynamo operating on scales that dwarf human comprehension. A machine built by gravity and time to process hydrogen into magnetic chaos. A world where the distinction between atmosphere and interior dissolves into irrelevance, where solid and liquid and gas are human categories that break down under conditions we can barely simulate. Every discovery Juno transmitted challenges the assumption that we understand planetary physics. The dissolved core, the asymmetric magnetic field, the geometric arrays of polar cyclones, the subsurface magma ocean on Io, the saltwater sea beneath Europa's ice, the Great Red Spot extending 320 kilometers deep, the radiation belts powerful enough to destroy spacecraft, and sterilize moons. None of this was predicted. None of this fits cleanly into models developed before Juno arrived. The spacecraft was designed to answer questions. Instead, it revealed how little we knew to ask. Consider what Jupiter represents in the broader context of planetary science. Gas giants are common. Exoplanet surveys show that roughly 30% of Sun-like stars host giant planets. Many of those planets are more massive than Jupiter. Many orbit closer to their stars, where conditions are even more extreme. If we cannot fully explain Jupiter after decades of study, our understanding of exoplanets is necessarily incomplete. We observe exoplanets through transits and radial velocity measurements. We measure their mass and radius. We infer their density. We detect atmospheric absorption lines and claim to know their composition. But we have never seen an exoplanet's surface, never mapped its magnetic field, never measured temperature at depth, never observed its moons. All exoplanet characterization is inference built on models calibrated using solar system planets. if those models are wrong for Jupiter, they are wrong for exoplanets too. This is not a minor technical issue. This affects fundamental questions about planetary habitability and the distribution of life in the universe. We search for biosignatures in exoplanet atmospheres. We look for oxygen, methane, phosphine, molecules that might indicate biological processes. But those searches assume we understand atmospheric chemistry, that we can distinguish biological signals from geological or photochemical processes. Jupiter's atmosphere revealed that ammonia and water are distributed in complex three-dimensional patterns driven by dynamics we did not predict. If we missed this at Jupiter, what are we missing at exoplanets where we have far less data? Europa's ocean might be habitable, it might contain life, but Europa sits in a radiation environment that sterilizes its surface. Any biosignature we detect must survive bombardment by high-energy particles or must be protected beneath ice or within plumes. The same is true for exomoons orbiting giant planets around other stars. Those moons might have oceans. But if they orbit within their planet's magnetosphere, radiation might prevent surface biosignatures from accumulating. We are searching for life with models that might be fundamentally incomplete. The existential weight of this realization is crushing. Humanity has one example of a planetary system that we can study in detail, our own. We have invested billions of dollars and decades of effort into exploring this system. We have sent spacecraft to every planet. We have mapped their surfaces, measured their fields, sampled their atmospheres, and yet we still cannot explain basic features of Jupiter's interior structure. What hope do we have of understanding systems we can only observe as flickering points of light? The honest answer is very little. We are cosmically ignorant. Our models are approximations built on incomplete physics. Our understanding of planetary formation is constrained by observing only one outcome. We know that planets exist around other stars. We know their approximate masses and orbits. But we know almost nothing about their interiors, their magnetic fields, their moons, their atmospheric dynamics. We are astronomers, staring at shadows on a cave wall and claiming to understand the objects that cast them. Jupiter humbles us. It reminds us that nature is under no obligation to conform to human intuition. A planet can have a dissolved core. A magnetic field can be asymmetric for reasons we do not understand. Cyclones can arrange themselves in geometric patterns. Moons can have subsurface oceans of magma or water. Radiation belts can accelerate particles to 99% of light speed. These phenomena exist whether or not our models predict them. The universe is not obligated to make sense to us. It simply is. And Jupiter is not done revealing secrets. The mission will continue until September 2025. Juno will complete additional orbits, conduct more flybys of Io, measure the magnetic field with increasing precision, map atmospheric dynamics at high resolution. Each orbit adds data. Each measurement constrains models. Each discovery raises new questions. When the mission ends, Juno will dive into Jupiter's atmosphere. The spacecraft will transmit data until atmospheric friction tears it apart. Those final measurements, recorded during the descent into Jupiter's clouds, might reveal phenomena that only exist at the boundary between space and atmosphere. Or they might show nothing unusual. Either way, Juno will die fulfilling its purpose. Observation, measurement, transmission. The scientific method carried out by a machine destined for annihilation. But the data will survive. Engineers will archive every measurement. Scientists will analyze observations for decades after the mission ends. Graduate students not yet born will write dissertations using Juno data. The spacecraft's scientific legacy will outlast its physical existence by centuries. This is humanity's approach to cosmic ignorance. We build machines, we send them into environments that would kill us instantly. We command them to observe and measure and transmit. We sacrifice them to obtain knowledge. And when they die, we build more machines and send them deeper, farther, into more extreme conditions. We are a species that throws technology into the abyss to see what screams back. Jupiter is screaming, The data it returns through Juno is a message written in magnetic field measurements and gravitational perturbations and infrared thermal maps. The message says, "You do not understand me. You thought you did. You were wrong. Your models are incomplete. Your theories are approximations. I am stranger than you imagined, more complex, more violent, more alien. And I am not unique. Billions of planets like me exist throughout the galaxy, each one a mystery. Each one a challenge to human comprehension. Each one an opportunity to discover how little you truly know. The abyss is not empty. It is filled with gas giants and ice giants and super-Earths and hot Jupiters. Worlds that orbit red dwarfs and yellow stars and binary systems. Planets with atmospheres of hydrogen and helium and methane and carbon dioxide and silicate vapor. Moons with oceans beneath ice, or magma beneath crust, or nitrogen lakes on their surfaces. Magnetic fields and radiation belts and auroras and storms. Structure upon structure upon structure extending outward through the galaxy in configurations we have barely begun to catalog. And we have studied exactly one gas giant in detail. One planet out of billions. We have sent one spacecraft to peer beneath its clouds and map its interior. And that spacecraft revealed that even our closest gas giant neighbor is fundamentally alien. What horrors await in the systems we have not yet explored? This is not a question driven by fear. It is a question driven by awe. The universe is vast, complex, indifferent to human understanding. We are temporary inhabitants of a small rocky planet orbiting an average star. We have existed as a technological civilization for less than 2 centuries. We have barely begun to explore our own solar system. And yet we peer outward into the cosmos and claim to understand how planets form and evolve and die. Jupiter is the correction, the reminder, the evidence that our understanding is incomplete, that nature operates on principles we have not yet discovered, that physics in extreme environments produces phenomena we cannot predict from theory alone. The only path forward is observation, measurement, data. More missions, more spacecraft, more decades of patient exploration. We must send probes to Uranus and Neptune. We must map their magnetic fields and measure their interior structures. We must land on Europa and drill through the ice and sample the ocean. We must return samples from Io's volcanic plumes. We must orbit Saturn's moon Titan and explore its methane seas. Each mission will reveal new mysteries. Each discovery will challenge existing models. Each measurement will constrain the parameter space of possible planetary physics. Slowly, over generations, we will build a more complete picture, not through sudden breakthroughs, through accumulation. Data point by data point, measurement by measurement, spacecraft by spacecraft. This is the only way to understand the universe. Through observation, through patience, through accepting that we are cosmically ignorant, and that knowledge is earned through sacrifice and effort, and the passage of time. Jupiter will be there, spinning, generating magnetic chaos, torturing its moons, broadcasting radio waves across the solar system. Long after Juno dies, long after the current generation of scientists retires, long after you stop hearing this, Jupiter will endure. A giant planet that will outlive Earth's biosphere, that will persist until the sun becomes a red giant and engulfs the inner solar system. That might survive even that catastrophe if it can avoid being swallowed by the expanding solar envelope. 4.5 billion years old, and it will exist for another 4 or 5 billion more. A planetary-scale experiment in magnetohydrodynamics, running continuously for the entire main sequence lifetime of its star. An experiment we have observed for barely a century. A fraction of a fraction of a fraction of Jupiter's existence. We are witnesses to processes that dwarf human timescales, observers of phenomena that challenge human comprehension. Temporary inhabitants of a cosmos that will continue long after our species vanishes. Jupiter does not care if we understand it. It does not care if our models work or fail. It does not care if Juno lives or dies. It simply exists, spinning, churning, generating magnetic fields and crushing hydrogen into metal and torturing moons with tidal forces. And we care. We send spacecraft, we build instruments, we measure and analyze and theorize, we try to understand. We fail. We revise our models. We try again. This is the human condition projected into space, the need to know, the compulsion to explore, the refusal to accept cosmic ignorance without fighting against it. NASA found something inside Jupiter no one saw coming. They found a dissolved core, an asymmetric magnetic field, polar cyclone arrays, subsurface magma on Io, an ocean beneath Europa's ice, a storm 320 kilometers deep, radiation belts powerful enough to kill machines. They found evidence that we do not understand planets as well as we thought, that our models are incomplete, that nature is stranger than our theories predict. They found the truth, and the truth is humbling. If you want to understand the universe, subscribe, because this is only the beginning. More discoveries are coming. More mysteries will be revealed. More missions will fail and succeed and transmit data that challenges everything we believe we understand about how worlds work. The abyss is staring back, and it is telling us we have barely begun to see what lies inside.